Mr. Qin Liu, Chief Scientist of Speech Semantics from Decision Making and Reasoning Laboratory. Mr. Jianye Hao, Director of Decision Making and Reasoning Laboratory. Mr. Fan Fan, Director of Acoustics and Audio Technology Laboratory. Mr. Hongbo Zhang, Chief Scientist in Autopilot from Decision Making and Reasoning Lab. Mr. Feng Wen, Director of Montreal Research Center. And Mr. Dahai Li, Co-founder and CEO of ModalBest. And Mr. Richard Peng from Carnegie Mellon University. Mr. Benyo Wang from the Chinese University of Hong Kong, Shenzhen. These two professors are also today's conference speaker. Mr. Ken Wang from Zhejiang University. Mr. Xiaojun Wu from Tsinghua University. Mr. Qingjian Zhang from Peking University. And Mr. Chunan Zhou from Nanjing University of Aeronautics and Astronautics. Thank you all for coming to today's conference and the follow-up closing ceremony. Now let's welcome Mr. Haipei Zhu from Huawei to give a speech first.
Good afternoon, honorable guests, our distinguished youth scholars, and also my colleagues. First, it's my privilege to express my warmest welcome to all the participants who join this afternoon's conference. I think through 3 days journey, most of you maybe realize that we hold this event by purpose. So we're gathering all the challenges, real challenges in the industry, and we ask people, the best, gather all the people around the world. They are best in competition, programming, things. And also we ask the most talented people in the academic to join this conference. We think that the three of these kind of people, when they work together, when they facing the challenge, maybe the real innovation will happen, and we are very promising to see that the real big breakthrough happened here. So I give some background of our, my work. So I work for CloudBU since 2017. So since the first day of our CloudBU, the technical strategy for the cloud, I think is maybe for the most of our Huawei's business units. That is openness, collaborating, and also innovation. So, for example, for CloudBU, we invest more than 40 million RMB, in a corporation. So we have hundreds of the projects that's collaborating with the professor, with the academic, with the industry all over the world. And also you know that we are in an age that maybe the AGI will break through. A lot of technology actually happened in these days, especially in the data center, in the cloud infrastructure. So in the Huawei cloud, the intelligent computing resources already exist in the general computing last year. So if you imagine that, the most infrastructure, the most technical stack may be changed in the 2 or 3 coming years. So that's a huge opportunity here. So that's why for CloudView, we value the competition talents very much. So for example, for this year, we already give more than 200 offers to the program competition talents. I think half of them is like global competition winners. We also have more than 10 overseas labs. So we hope the winners of this competition can also join us in overseas labs. It's also, we hope that, yeah, it's also our hope. And also for the technical, we know a lot of the challenge happens here. For the data center, just as I mentioned, the intelligent computer resources already replaced the general computing. And the normal distributed system is only like thousands of nodes together. Today you will see like the AI system, not only for the training, but also for inference, is like 10,000 of the nodes, high scalable system. And also there's a lot of the algorithm, a lot of the hardware, software, synchronized design will happen in a large AI system. So I think that's a lot of the opportunity for the industry, for the academic, and for our competition tenants that we can do in this area. And also I heard that the Universal Cups, I would thanks to Universal Cup, and I think that's it's the second year we have cooperating on that. Last year was very successful. We hold an event in Mexico, I think, right? So this year, I think the second time, so I think the community grows very well, and the Universal Cup not only be a competition, organization, but also it's a bridge that connects the industry and all these talent competition programmers. So I think this afternoon we'll have like a very full schedule of all these topics, and I encourage all our people, especially our Huawei people, to join the discussion, fully participate, and this may be a potential chance that for the future cooperation. Again, thank you for all the people that joined here. I hope that we have a productive meeting. Thank you.
Our conference officially begins now. Let's welcome Professor Richard Peng to give a talk. He's an associate professor of Carnegie Mellon University. His research interest is in the design and analysis of fast algorithms for solving fundamental computational problems, including graph algorithms, dynamic algorithms, and linear algebraic algorithms. He received the 2021 SODA Best Paper Award and the 2022 FORTS Best Paper Award. He also has won IOI gold medals, ICPC World Finals medals in his competitive programming career. Today, his presentation topic is linear system surprises. Let's welcome.
Test. Does the sound work? Awesome. Okay, I'll start. Okay, so I'll talk about some perspectives on continuous algorithms through linear system solving. So first, a bit about me. So like many of the contestants, I learned a lot of math and algorithms from doing contests. But for some reason or another, I couldn't really stay in contests. In particular, I had to go get a PhD in order to stay involved as an organizer. The result of this is that a big chunk of my research actually draw ideas from the OI literature. And sometimes it's actually a little hard to talk about them to a kind of a more research setting. So first, I would like to give a huge thank you to the organizers for this opportunity for me to try a new talk among more familiar friends. Let me start with a problem from the course that I'm teaching, which is I have an escalator that's moving upward steadily. If I walk at 1 meter a second, I get to the top in 20 seconds. If I walk at 0.7, it takes me 25 seconds. How long does it take to get to the top standing still? How many have seen this problem? Have a show of hands. How many have done this problem before? I'm sure that this is not how you all set it up, but if you give this problem to a typical CS student, the way they will set it up, they will make it 2 variables. Length of the elevator, its speed. And then the 2 given conditions translate into fractions. And this is where people really mess up their algebra. They would say like L divided by 1 minus V, L divided by 0.7 minus V equals something, and then they subtract the equation, they get a huge quadratic mess, and everything becomes very interesting. If you've done this kind of problem before, you know that the main trick for this problem is you keep everything linear. So the way to deal with fractions is you really write them out. You expand everything, and you write it out as everything on both sides has power 1. And once you have 2 linear systems, right, you solve a system in 2 variables, first power, and then you solve for L, you return some values. At that point, it's all systematic. For people who have done contests, it's probably a little surprise to you that the typical average on such problems is below 70% in a CS major, in a discrete math course for CS majors. I can make a very long argument to you why this is okay, but I feel there's a very important takeaway from this, which is that for a lot of very natural problems, the natural way we model them is often not linear. But in many cases, for example, in things like differential equations, in things like linear programs or operations research, and nowadays in things like data science, one of the key tricks in making the problem more computationally feasible is to keep everything linear, is to write down the conditions in a way that all you get back is a bunch of linear conditions. And that's what I really want to talk about in this talk, which is that linear systems can be used to solve a lot of things. And the other way also holds, which is that all your favorite tools can also be used to solve systems of linear equations. Let me now move on to a contest problem. This is from NWERC 2017, and it's called a abelian sand pile model. What this is I have a unit weight undirected graph, and at the nodes I have some tokens. And then it repeatedly does the following process, which is for a vertex that's not a sink, as long as it has more tokens than its degree, it sends 1 to each neighbor. So here the first vertex has 3, its degree is 3, so it sends 1 to each neighbor, the sink gets 1, the other 2 vertices become 2. And now the vertex in the triangle, now it has 2 tokens, more than at least its degree. Sends 1 to each neighbor, now it becomes 3 and 1. And then the 3 sends 1 to each neighbor, and now it stabilizes. I won't have time to talk through this, but it turns out for this, any way you topple actually gives you the same result. So there's a very natural question about computing on a sand pile process, which is given a sand pile problem, so given the initial graph, the number of tokens on each vertex, I want to find this final state. And this is actually a very well-formed computational problem because no matter how you do it, the result is unique. And you can actually formulate this as a linear inequality in integers. So the way you can write a linear system from this is you let xu be the number of times vertex u topples. And now you look at how many are left in the vertex. What you have is that you have the starting number plus the number you received from its neighbors. So that's the sum over all your neighbors of their x value, minus the number of times you topple. So that's degree of u times x of u. And the termination condition is just that the number you have remaining is between 0 and the final state. So in this example here, the number of topples per vertex is 1. And then you can see there on the bottom left vertex, the resulting number is 0. The calculations work out. So from these linear inequalities, there's a very natural question, which is, could we compute sandpile faster? There's a couple of surprises. First one is that the solution, if you just write out these inequalities in integers, the answer is actually not unique. Takes a little bit of work, but you can actually construct a sandpile problem where there exist two vectors x which both satisfy these inequalities. The even bigger surprise is that despite a whole bunch of us trying fairly hard to try to solve this faster, there's nothing for this problem currently that's faster than just directly simulating it. I mean, I see a couple of people already kind of look at each other and go, maybe I can do something faster. I'll be very interested if there is something, either like a better upper or lower bound for this problem. But in our current understanding of it, what this really means is that for many natural problems on networks, there's nothing better than just directly doing local simulations. There's nothing better than just look at a vertex, send things to its neighbor, repeat. And this leads to things like the PageRank vector, or people blaming each other. Right? So you get many settings where some kind of local algorithm is extremely necessary. It also says that for many of these integer problems, maybe the continuous relaxation is actually a little easier to study. So the next natural problem that I was looking at was what happens if we look at sandpile in the limit? And this is actually stuff that Gaoyu worked on at some point, which is what happens if I just have, as the number of starting sandpile location tends to infinity, what happens to the final state of the problem? Or like, what is a rough total count at every vertex? And all of a sudden there, the inequalities become inequalities, right? Because the amount you're off by the degree is actually very negligible. So what you have is for all the intermediate vertices, what you have that the sum of the xu's minus its degree equal to 0. And this is now a linear equation, and this actually makes a much easier problem to solve. So this is getting to a point where for a problem that is extremely hard discretely, we have a continuous analog where it is actually significantly easier to solve. And this is actually one of the reasons we like to use continuous algorithms. The reason is that continuous routines can often be solved much faster. They also have this kind of situation where you don't have these nasty local minimas. So you actually give more structured answers from looking at more continuous routines. So continuous routines actually show up throughout algorithm design. They show up in things like approximation algorithms, and they in turn get used in like areas like cryptography. In optimization, the continuous formulations leads to things like incentives and so on, leads to also things like game theory. And statistical models is kind of a way to write down probabilities for everything that underlies a big chunk of modern learning theory. As somebody with a kind of more background in discrete algorithms, the way I like to understand continuous algorithms is by looking at graphs. So the continuous graph subroutines, again, on graphs, there's this phenomenon which continuous subroutines can be solved much faster, and they tend to give much more structured answers. So over the last decade or so, there has been a lot of work on getting faster graph algorithms using some kind of continuous method. So some examples of continuous algorithms are things like bounding the sandpile total counts. They can be used to do subgraph or cut detection. And the most surprising one is that for some data structure problems even, we now use continuous algorithms. I'll get to that in a second. But first, let me say that how would a continuous algorithm try to solve the sandpile problem? There's this idea from the early 90s that ended up being very influential in modern algorithm design, which is this idea from Vaija, which is that all I do is use the fact my matrix is coming from a graph. Right? I wrote a linear system that is motivated by a graph. So I might as well try to do some graph theory on it. So the very influential idea by Vaija is I find a good spanning tree, and then I adjust the solution via the tree. This idea, of course, went through many iterations. But one of the simplest iterations is versions of this is by Kellner, Orikia, Sitford, and Zhu. And what they say is I have a tree, right? So all I do is I just repeatedly sample the non-tree edges. I pick a non-tree edge. That non-tree edge creates a cycle on the tree. I adjust my solution by that tree cycle. I repeat. And the remarkable fact that they proved is that if my graph has m edges, sampling something like m log n cycles gets me to a solution that is very high quality. It basically gets me a solution that is accurate to machine epsilon. And for the programming contest people here, now you know what to do, right? All you do is you do throw some tree data structure at it, and you see what happens. But first, let me try to describe how does the KOSZ view of the world work. What they need is they need to, because there is something like m log n iterations, what they strongly rely upon is the idea of energy. So given a graph, they need this kind of ability to define an energy function. And this is where what you do is you take your linear problem and you relax a little bit. So what I want for the solution, right, is I want, remember for the number in minus number out equation, right, what I do is summing over all neighbors of xu minus degree times xv, that equals to the starting point. There is a very simple potential function you can write down for this. I take the difference, I take its square, I minimize that. This is a convex function. So for those who are familiar with gradient descent, what you say is that you can just kind of you do almost anything, you get to the minimum. And there's something called cache-match method that does exactly this. Cache-match method, what it does is it picks one xu, looks at all the xv's, bring that xu to the minimum, repeat. This version of cache-match is actually a little hard to realize as a data structure. I mean, it's actually a pretty good programming contest problem, how to realize this version of the cache-match method. But it says that there's a kind of an energy minimization version of looking at linear systems as well. So we started off with the local method version. This is the energy minimization version. What it is this kind of the SGD version underlies something like stochastic gradient descent. It's that I have a bunch of functions, f1 to fm, defined on n variables, all of which hopefully are convex, just to make it easier to do gradient descent. And what I do is I want to output a vector that minimizes the sum of these functions at x plus some linear term in terms of x so that you get the right-hand side encoded there. There's this kind of very kind of subtle fact for convex optimization, which is that actually minimizing a convex problem is actually equivalent to solving some kind of linear equation. Well, I mean, general convex functions, the derivatives are not linear. But you can take this view and can generalize it. But in general, when you have a sum of convex functions, minimizing their sum is equivalent to solving some system in a gradient. So the reason this happens is that convex functions, for those familiar with convex functions, right, is this kind of bowl shape. And anytime I have a derivative, all I do is I just walk downward a little bit, and the solution will get better. So the only thing that you really need to worry about once you have a convex formulation is how fast do your things converge. So the difficulty in this is you must be able to take sufficiently large steps. For the more kind of programming contest-minded, I should also mention that this is kind of one of the solutions that typically it's very hard for data setters to guard against. I know at least like 2 or 3 world final geometry problems where you just write down a proper energy function, and you just do descent on it. Like the best example of this was WF12 problem H. I think that was a zero solver. I think there was like 4 attempts on that total. You just write down like a 30-line like energy function minimization, run for like 10 to the 6 steps, and it will actually converge. Well, of course, like the fact I say that probably means that the judges in the crowd are probably saying, like, oh, we should check this in the future as well. But I guess that's programming contest for you. So the difficulty in designing this kind of energy minimization algorithm is what do I set as energy? Right? So the KOSZ energy is actually significantly simpler. It's actually even simpler than the difference of the degree u minus the sum of v. It's actually an extremely simple function. What it is take all pairs of neighbors, xu minus xv squared. Why does this make sense? So this is actually useful to think about the derivative of this. The derivative of this is it's a square, right? So the derivative is just xu minus xv. What is the sum of the derivative at xu? It is just sum over all v of xu minus xv, which translates into degree of u minus the sum over all neighbors of xv. It actually exactly recovers the in versus out equation we had earlier. So the gradient being 0 is still the same as the equation at u being satisfied. But the point here is that there is an exceedingly simple energy function, which is just sum over all neighboring pairs of the difference squared. That lets you define one of these kind of energy minimization view of linear system solving. There's also another reason this is super nice. The other reason is that those familiar with electrical theory, or those who have done some kind of resistance problem, you recognize that xu minus xv squared is actually just the energy of what happens when you put a voltage of x on every vertex. Like imagine you take your graph, you make an electrical circuit out of it. And on every vertex, you hook a battery. You either have positive or negative voltage on it. Ohm's law says that the energy of an edge, so Ohm's law I put on the bottom right, but Ohm's law roughly says that the energy of a resistor is just the difference squared divided by the resistance. So what you get is this is actually exactly the energy of the circuit. But once you think in terms of circuits like Kirchhoff's law, Ohm's law, and so on, it also says that because I have an electrical circuit, right, I have flows. And what you actually have is that the electrical circuit itself also forms a flow. It takes a little bit of work to check, but once again, you can check by gradient. But essentially what happens is that the corresponding electrical flow is just summing over E of RE squared. It actually is roughly what you think it is. It's just the resistance times the flow value squared. So now my graphs can actually be viewed as electrical networks. And the KOSC algorithm, the kind of the exact formulation of it, it actually is interpreting things in the flow space. What it actually does is it takes the current flow and looks at the cycle and says, I want to either adjust the cycle forward or adjust the cycle backward. And all I need to do is bring the cycle to its minimum energy configuration. So this is like your standard link cut tree. You can actually do it with HLD with enough work. There's also a dual version of this for cuts as well. But the funny thing coming out of this is that this is linear, right? But what if I define this for other functions? As it turns out, pretty much every graph optimization problem we know can be formulated like this. All you have to do is find a pair of dual functions, this psi up there and this phi down here. Well, phi up there, psi down here. What you have is you have a convex function on every edge, and you minimize something depending with some boundary conditions. What that lets you do is actually lets you do things like image recognition, image denoising. It also lets you do things like planarity testing. There's this kind of a very funny planarity testing algorithm, which is all you do is you just put some vertices down, and you let everybody else go to min energy state. That actually does planarity testing as well. In the dual setting, what you get is you get things like VLSI design, routing, auction, and then the earlier example is things like Wasserstein-Gahn is actually doing this kind of routing as well, but with a different energy function. And a lot of the progress in graph algorithms in the past, say, 5, 10 years was kind of really by looking at these kind of formulations and then thinking them in conjunction with data structures. The current state of the art in that space is kind of using kind of energy minimization view is probably best described in terms of the APIO22 problem, which is I have a directed graph. Either I have edges coming in or I have edges leaving. And all I have to do is you tell me when there's a cycle. With a little bit of work, everyone here can probably work out the offline algorithm. The offline algorithm is a little bit of a challenge, but you can actually work out by doing a binary search on time or something. You can actually work out an offline algorithm that's linear time for this. But then I force you online. I force online. I think the APIO problem actually forced online. It's basically the problem asks you, as the edges come in one by one, tell me when does a cycle form. Or as the edge deleted, tell me when the graph is topologically ordered. For some very strange reason, the current best data structures we have for detecting both of these go through this kind of energy minimization view. What they do is they convert the problem by writing down suitable potential functions into this kind of undirected problems, and they do some tree data structures on top of it. Let's just say they're fairly long archive papers within the past year or so. So let me I have a little bit of time, so let me just say a little bit, go back a little bit, and I'm sure you have all tried to read, some of you have tried to read this kind of results, right? So there's a serious question like, what is going on? Like, why does a simple problem like incremental cycle detection require like 140 pages of writing? So first, let me if you look down there, right, this is kind of the typical kind of thing that happens at like page 60 of your proof. It's like my algorithm has like 3 pieces, there are like 3 parameters on k, and now I balance this like horrible expression in terms of k. And what comes out here, if you do a little bit of work, it comes out to something like m to the 1/2 3 over 2 minus like 1 over 328 or something like that. Here's how I like to parse what happens. So what happens here is that these kind of results, what they let you do is they let you combine 2 or 3 theoretical ideas in one go, right? You have to write an optimization formulation. Sometimes you have to get data structures. Sometimes you have to get data structure to happen online. You have to kind of de-randomize, make deterministic data structure, and so on. So there's a lot of work in this that happens, and a lot of them happen kind of in a very theoretical setting. And I claim the reason this happens, this is very useful for those who want to get into research, is that in my experience, pretty much everyone who showed up to research only really want to do one thing. So for those, how many from SJTU know Chen Se still? So the SJTU algorithm professor says basically, I only want to do lower bounds. And then a student who worked with him showed up saying, I want to do lower bounds. Gao Yu took a class from Yitong, and Yitong says, I want to sample everything, so Gao Yu now samples everything. Then there was somebody who showed up who likes to claim that every inequality problem is trash, but he still likes to just throw Cauchy inequality at everything. Then I had a student show up that only wanted to do HLD for an entire thesis. And then both Jingbang and I think we both went to grad school with the mentality that we really like trees. Doesn't have to be HLD, but as long as it's trees, it's fun. In a lot of settings, what these problems really are, like when you get to the kind of energy minimization framework, what you're looking at is you're looking at one of the most robust settings for writing down a graph problem. So what you get to when doing this kind of work, like this is kind of where like algorithm design kind of meets math. And in math, kind of the most important thing is this kind of robust formulations. You want formulations that is basically easy to tweak, formulations where it can sustain some errors, formulations where like if you like make an error of like factor of 10, you just run the problem 10 times and it will converge. And what this kind of setting lets you do is it first lets you kind of quantify how much you're off by. So for example, if I want something like a polylog n approximate max flow, this was known in 2010. So a lot of like the work in the last like say 12 years was really just to get that thing to work with like a better error dependency in some sense. And then the thing is once you have things quantified, you can kind of try to make up for the kind of the gaps in understanding. It's a kind of a very kind of theory research mentality. But what you do is then you kind of make up for gaps in your understanding by either kind of improving the existing tools or even just go develop entire new tools. Sometimes you'll actually have to go develop an entire new algorithm idea based on like what's missing in the proofs. So this is kind of what I like about the kind of the numerical way of thinking about linear systems, which is that because there's an energy function, it gives you one of the most robust way to think about things. And then, but then let me get to the setting with linear system solving problem everyone's most familiar with it, which is the matrix view. Right? This is probably how most of you learned how to deal with linear systems. So this is what you get is you write down a matrix and you solve a linear system in that matrix. And for the graph problems I've been talking about, there's actually a very systematic name for it. It's called a graph Laplacian matrix. The way you get that matrix is you put the degrees on the diagonal, and then for every edge, you put the negation of its edge weight on the corresponding U and V entry. So I put the off diagonal, I put the negation of the edge weights on there. So the algebraic view of linear system solving is basically now I have a matrix A, I give a vector B, I want to produce an X such that AX equal to B up to some errors. And the way that you probably have all heard about doing this is to just invert the matrix, right? Every team has some kind of Gaussian elimination in your notebook, right? Does any team not have Gaussian elimination in their notebook? So this in high-performance computing land, this is known as direct methods. The idea is basically you directly modify the system to one where you know the solution, so some kind of QR or like LU factorization. And these things actually, they run fairly well, and the problem actually for them is actually the space limitations. There's a couple of surprises with direct methods as well. The first and foremost is that Strassen showed that, first of all, this is equivalent to matrix multiplication. But also that the matrix multiplication exponent is not 3. It's actually something slightly below 3. Well, it's not even slightly. So Strassen showed something like 2.87, log base 2 of 7. But then since then, by doing more recursion, people actually have gotten the bound down by a lot. Kind of what the next big surprise was Coppersmith-Winograd in 81 showed that it's less than 2.5. They got to 2.49. And then there's a lot of work, some of which actually goes into more recent kind of even this year. I think even this SOTA, there was a further improvement on this, And the current best bound is something like 2.372. This is a very active area of work. The thing that is actually kind of not often said about kind of the role of omega is actually that for different ranges of omega, you actually get different algorithms. For a lot of things like linear programming and also some graph problems, if omega is bigger than 2.5, omega is less than 2.4, and omega is less than 7/3, the bounds actually significantly change. Like what is your best algorithm actually significantly changes. So there actually are situations where like for the Strassen algorithm, which is actually known to be practical, that you actually want to have a slightly different algorithm than like just using Cooper-Smith-Winograd, which is the also the tensor rank based stuff. And then the question there actually I don't know about is what happens if it's about 2.35? Does any kind of qualitative change happens about 2.35? And I feel this is what we need to take offline to seriously look at. I want to say a bigger surprise in graph algorithms, which is actually that if you run Gaussian elimination on graphs, what you get back is still graphs. So Gaussian elimination actually has combinatorial interpretations. There's a couple of very funny facts about Gaussian elimination. The first one is that when I eliminate two vertices in opposite order, if I eliminate one, eliminate two, or eliminate two, eliminate one, I actually get the same thing. This resulting thing is called a Schur complement. What does that correspond to on a graph? It corresponds to a smaller graph on a subset of the vertices. You can actually think of vertex sparsifiers almost like the second layer of a seg tree. They're actually just an equivalent problem on a subset of your vertices. And then you can get this kind of thing, which is that basically, actually the Chinese IOI TST has had this kind of problems in the past. But I think enough people complain that they don't exist anymore. But the general idea with this kind of problems is basically when you do elimination on graphs, you get back graphs. You can actually do some kind of like tree decomposition and so on using the fact that eliminating graph Laplacians get you back graphs. And then the next even more powerful fact is that graph Laplacians have sparse approximation. So you can actually do some kind of sparsified elimination and get back things that look not unlike seg trees. Let me just illustrate with an example exactly what happens here. So if I want to eliminate the first row here, what I want to do, right, I want to get rid of the -1 in the first column. What I do is I add 1/3 of the first row to the second and third row. If you look at what happens if we do the math, what you get back here is actually 11/3 on the off diagonal as well as on the diagonal. So formally what you get is what's called a Y delta transform. It's actually an extremely well-structured operation. What happens is if I have a vertex with neighbors with weights W1 to WD, and I eliminate them, the new edge weights is basically for every pair of them, I take the product of the weights divided by the total weight. So this basically all you do is when you eliminate a star, what you do is you create a clique on its neighborhood. And then a lot of these kind of, then a lot of details goes into how to kind of directly generate the sparse approximations and then have the errors accumulate in a way that's still under control. It still accumulates in a way that like overall you still get a controllable amount of error. But as I said before, like this actually lets you just kind of build seg trees on general graphs. And so the idea is basically you start with top layer, you eliminate something like all but like n over k vertices. You do this in something like n over k time, get a problem that's k times smaller. Repeat. It's not really a two-way seg tree, but like Yuhao likes to do like 16-way seg trees to my understanding, and this is roughly one of these things. You can set k arbitrarily. Advantage of this, it's actually a very simple algorithm. The algorithms at the end of the day look very much like random walks, but I won't be able to define enough math to get into the details of that. But it's simple, it's parallel. The huge limitation of this type of algorithm is actually not very robust. Currently, because it's relying so much on the structure of Gaussian elimination, kind of the active research in this area, what they all look for is they look for basically some kind of nonlinear elimination. This is where we get into like 100-page surveys to read about this. So kind of the first kind of systematic survey on this is in Gramos-Goranchi's thesis. But if you want like a representative result on it, Jing and Sun did a result that was basically able to maintain 10-edge connectivity. This is how I like to tell people, because the dependence on C is absolutely horrendous. But what they are able to do is in a fully dynamic graph, they are able to maintain whether two vertices are 10-edge connected. Yeah. And then Gao Yu, in his thesis, what he did was he made it kind of the fully dynamic electrical networks, basically, to the point where it actually worked pretty well with network flow algorithms. And this kind of the ideas from there actually has recently been used very heavily in dynamic spanners, dynamic routings. It's one of the key routines in modern dynamic graph algorithms. And of course, with a general kind of matrix algorithm, as I mentioned earlier with cache march method, right? Once you understood something really well on a graph, I think there's always the question of what happens on a general matrix. So here, there actually turns out there are actually general matrices that's also closed under elimination. And this leads to what, so like after I realized this kind of problems exist, I started reading about the 998244353 literature, actually to the point, at least to the point where I remember the number 998244353 now. But this in some sense is like the ultimate 998244353 problem. What you have is you have a matrix where if you shift it, if like displace it a little bit in one direction, the difference is low rank. This turns out to be a property that is actually preserved under elimination as well as inverses. This is called displacement rank. It's actually a little hard for me to define, but if you're interested in creating more 998244353 problems, I highly urge you to Google Cauchy matrices and hierarchical matrices. This is like one of the areas where programming contest understanding of these things probably exceeds academic research right now. What are these useful for? It turns out that if you combine this back with an energy minimization algorithm, combine it together with a Krylov algorithm, what you actually get is you actually get the current fastest solvers for solving general polycondition sparse linear systems. First, Santosh and I got a runtime that's like slightly below omega, and then Zipei Nie actually from the Huawei Paris lab got the current best runtime, which is about 2.27. But there's actually a lot of problems that's very interesting, both in terms of programming contests, also in algorithms research. It's kind of one of the areas where like contest really starts meeting research. So that's kind of a very kind of quick kind of overview of a couple of topics related to linear system solving. But the general kind of takeaway I want to give on this is that for a lot of continuous algorithms, especially on graphs, there's actually three ways to view them. You can either view them as local methods, where everything talks to their neighbors. You can view them some kind of global energy minimization with some kind of global potential. Or you can view them as some kind of algebraic operator theory. What these actually correspond to in mathematics, they correspond to differential equations, functional analysis, and just straight up abstract algebra. They lead to a lot of very new and kind of interesting approaches to fundamental problems in algorithm design. And often for problems that are very well studied and even different approaches for the same problems. It is actually, in my opinion, one of the most kind of interesting areas of algorithm research right now. That's all I have. Happy to take questions.
If you have any question, please raise your hand.
Hello, Pen. I have a question about the omega, the bound of omega. You show that there would be something change when omega is less than 7/3. There are two questions about omega. First one is there some non-trivial lower bound of omega? The first one. And the second one, what will happen if the omega go lower than 7/3, which problem will change the fastest algorithm for this problem, and will some other problem change when the omega go lower than 7/3? That's all.
Okay. So the question, as I understand it, is kind of more about the status of omega. So there have been some kind of conditional lower bounds, like if the current state of with the current state of approaches, but the result by Duanran and Zhou Renfei and sorry, I'm blanking out on the third author's name, but there was a result 2 years ago in Fox that kind of went below that lower bound. So there's actually a lot of kind of very interesting questions about like getting some kind of conditional or unconditional lower bounds of omega. For the bounds that I mentioned, so there's 2.4 versus and then 7/3. 2.4 is basically both of these are situations where the linear programming algorithms, so linear programming, what happens is that you're solving a sequence of linear systems, sequence of interrelated linear systems. 2.4 is when you can, a certain kind of inverse maintenance starts being effective, like start maintaining some kind of low rank factorization of the matrix. 2.33 actually has implications in both graph algorithms and sparse linear programs. So if it's below 2.33, I think you actually get faster. I think at that point, p-norm regression actually gets slower than some kind of, regression, because there's a conjecture in linear programming about whether iteration of linear programming is n to a third or n to the half. So depending on whether it's a half or a third, whether the omega is below either of them actually changes the linear programming algorithms. And I think the other one for 2.33 is some kind of shortest path maintenance or some kind of network connectivity maintenance.
Okay, any other question?
Thanks for the talk. There's a question about energy optimization algorithm when we take some spanning tree and then iterate over all of the tree edges. You mentioned that we want some good spanning tree to choose. What properties do we seek from the spanning tree?
Oh, this is a very good question. This is a major open problem in effective algorithm design. It's actually the spanning tree, what you want is what's called a low stretch spanning tree. Low stretch spanning tree, what it is you want a spanning tree where for every non-tree edge, you look at the length of the tree path. And what you want is you want the total length of all those edges to be small. Mathematicians actually have conjectured that the right average stretch is log n over 2. The current best bound is order log n log n with a very large constant. So there's actually quite a bit of room to work on here as well. Yeah, but practically finding this kind of spanning tree, in practice, you've typically heard of shortest path tree, you've heard of MST, but it turns out that spanning tree we actually want has some fairly different properties. Very good question.
Thanks.
Okay, any other question? Okay, then thank you, Professor Peng. Now, let's welcome Professor Ben-Yo Wang from the Chinese University of Hong Kong, Shenzhen, share his work. He's currently an assistant professor in the School of Data Science. To date, he has received the CDER 2017 Best Paper Nomination Award, the NACL 2019 Best Experimental NLP Paper, the NLPCC 2022 Best Paper, and the Huawei Spark Award. He also served as the Publicity Chair for NLPCC 2023 and the Website Chair for EM NLP 2023. The large models developed by his leading research team, including the medical health vertical field large model Huatuo GPT and the Arabic large language model ACE GPT. Today, his presentation topic is practice on medical LLMs. Let's welcome.
Okay, thank you for the introduction. I'm very happy to present my work on medical language models. I manually modified the title to trustworthy medical language model about everything. It's most about our practice to develop Huatuo GPT. And first, here's the roadmap. We have developed Huatuo GPT. Actually, we are very proud to say that we are the first vertical language model, which the first version was released in February of 2023. And that version, we call it Huatuo GPT because we want to respect the great physician Huatuo, which was 2,000 years ago in Chinese history. Later, we also released many data sets and benchmarking and different models for multimodality, for multi-languages. And also recently we have the one, Huatuo GPT 01, which instance the long reasoning, slow thinking 01 style reasoning paths for medical scenarios. Here we want to basically introduce how we develop HuaTou-GPT from the first version to the new O1 version, and how we deal with the different issues we have met in different stages. First of all, in the year of 2023, February, we first used some patient-doctor interaction dialogue system, dialogue data for existing language model. Previously, we used Pangu 20.6 billion, which was a smart model developed by Huawei. And that model, we try to train with human doctor-patient interaction dialogue data. But however, at that moment, the big backbone model was not work that well, especially the instruction following doesn't work, and people try to interact with the HuaTou-GPT, but in most cases, it doesn't get very coherent response. But later, we have a new open source model, especially from Meta, the Llama, which probably back into the March of 2023. And we try to use our data in Llama and start to behave like reasonable response. So we open source the HuaTou-GPT right after Llama. And as that model, the first thing we want to train for the model is to let the model talk like a doctor. If you talk to ChatGPT, probably they will give a response, but never ask. Not never. Usually doesn't ask any follow-up question. It just responds whatever you need. But when you talk to a doctor, the dialogue at most time are interactive, which means that probably they can also raise some question for the patients. And the two people, the two sides from doctor and patient, they can both of them could ask questions. Somehow in speech we call duplex. But however, the early version ChatGPT doesn't behave like a duplex model. We try to change the data. For example, from doctor's data, we make it more interactive. For the ChatGPT data, we tell the model to behave from a doctor's tongue. And combine both data, and we train with them using reinforced learning. And finally, we have the HuaTou-GPT version 1. And that model, I asked many medical experts to test our models. In some cases, the knowledge aspect is not correct, it's not satisfied. Some doctors complain to me why they give so much wrong information, misleading information. So we developed one benchmark we called CMB. At that benchmark, we mainly borrow some examinations for medical students and medical doctors. It's like once students they enter the college to learn medical school, to learn medicine, and once a new doctor working in a hospital, and they also has to learn some new knowledges and take many examinations. So we collect all the examinations for medical doctors, medical students, and combine everything together. It became the CMB benchmarking. And the CMB benchmark we host in an online website. If you access this website, probably you can see a lot of models ranking in the leaderboard. But just one issue we have to highlight is that the top ranking model, they get accuracy more than 95%. Which means the model nearly know everything about medical knowledges. But true is that probably there's some data leakage issue because every data we collect is from the public examinations. They probably have already been in the training corpora for those models. So later we will explain how we can overcome the data contamination issue. Because we found that model lack the medical knowledges, so many misleading information coming out from our model. So we want to inject some medical knowledge at a scale. Knowledge. For example, we could have many data they from internet, from the books, from Wikipedia, from whatever text copper, they may in different languages, how we could train our model with different kind of data. The data, the format, language, and the topic may be different. Our training protocol is quite simple. As we first use a language model, probably could be a ChatGPT or the model trained by ourselves, and we transform the data from different languages, different formats, to a uniform input-output pair. The philosophy between training from plain copper and input-output pair is that the latter is learning the mapping from input to output. We have already checked the data from our synthesized input-output pair. Most of them, like 30%, they are causal questions. But if you directly learn from plain copper, most of them are some word correlation. So we argue that probably using those input-output pair, we are more likely to learn some high-level causal questions with more close relation between input-output. Probably learning efficiency could be higher. So we combine those input-output pair and our supervised fine-tuning data. The data format or type between pre-training and the fine-tuning will be the same with instruction, input, and output. If we check our training curves, we could see the training process is very smooth compared to the two-stage training because the data are unified with a very simple protocol. When benchmarking our model, as an experience we have known for the CMB benchmark, we know there are so many data contamination issue for benchmarking. So we collect a new data set, very fresh data set. It's the national pharmacy examination. The examination was happening in October. We test our model right after October, like November, and there's no there's no enough time for every model, every company to have this data in their training copper. So we could argue such a benchmarking is quite fair and clean. And as we can see here, from this line, we could see our results. The left group is for the Western pharmacy, and the right part is for the traditional Chinese medicine. In both examinations, we are the first model that get more than 60% accuracy, which outperform GPT-4 and Wenxinyi and many other open source models in China and also Westerns. And we also test the performance in this year because everything happened before what was in 2023. And in the year of 2024, we have another round of national pharmacy examination. So we test our model again. As we can see, the second last row is our Huawei GPT-2, which was 2 years ago. And we are still past the pharmacy examination in this year, and slightly lower than Qianwen 2.5. But Qianwen 2.5 is much larger and like 1 year later developed compared to Huawei GPT-2. So we could argue Huawei GPT-2 is also competitive, even it has trained 2 years ago. Okay, sorry. But now people not only care about accuracy, they all want to know how much confident the model will give the results, how much we can trust such an output. So we developed one paradigm called a chain of diagnosis. This is borrowed from a traditional chain of thought, which means we not only care about output, we also want to care the reasoning path, how we could get such a response. In the chain of diagnosis, we design a structured chain of thought. Typically, it's like when once a patient raises a question, probably first we want to know how many or which symptoms the patient have mentioned. And then we want to pre-ranking some possible disease. Could be A, B, C, but we don't know, maybe four or 3 to 10 different possible diseases. And then we let the model to do a reasoning. This is maybe a typical chain of thought reasoning. After that, we will have a confidence assessment for each of the candidate disease. If the top ranked disease is with high confidence, we just output such a diagnosis results. Otherwise, we're going to have another round of questioning to get more information for a higher confidence response. Interestingly, this paper was 3 months earlier than OpenAI 01. So we just used some predefined structure chain of thought. But in 01, they probably have more diverse reasoning paths. As you can see, we have a clear stage 1, 2, 3, 4, 5. This is usually similar to the process for doctors. But once 01 was out, we realized that probably we could let the model generate more diverse, not predefined by human prior, but more compatible with the computer thinking style. After 01 is out, so we give the Huawei GPT-01 implementation. In such an implementation, we want to introduce one concept. What is like it is the verifiable medical question. Is that we have one question. We do not need to give the clear reasoning path. We just we just want to develop a verifier to tell the model whether your answer is correct or not. We only care the answer is correct or not. We don't care how the model gets the output. They may have different kind of reasoning paths, but we do not matter too much because we want the model learn how to thinking by himself. So if we have the verifier to check the answer is correct, then we can train the model with synthesized data with reinforced learning, because reinforced learning only needs the rewards. They do not necessary to give the concrete reasoning path. Follow this philosophy, we first collect a large collection of verifiable medical questions, and we let some models, could be any model you have, to generate different kind of chain of thought reasoning paths. And if the answer is wrong, this is given by the verifier. The verifier could be an easy rule-based system like answer extraction, answer matching, whatever. And if the answer is incorrect, then we let the model thinking with another round. They could use like backtracking, new trajectory, or verification or correction, whatever path the model could use. And until if we finally get the right answer, we keep the data. Otherwise, we just remove such a data. This is what we have done for SFT. For the second stage, reinforced learning, that's much more easier because the verifier will directly give the rewards. So we train the model with reinforced learning. Finally, we have our Huawei GPT-01 version. In this version, we try different kind of reinforced learning, including DPO, RAOO, and PPO. More recently, GRPO became more popular because of DeepSeek Math and also DeepSeek R1. But at that moment, we just test DPO, RAOO, and PPO. Most of reinforced learning could work very well because the verifier, the rewards provided by verifier could indeed work for such scenario. And we also try to scale in such a model, whether the 01 style reasoning could not benefit small model, but also larger model. We try to scale our model to 70 billion. It also get a very good improvement. And then we also try the national pharmacy examination we have introduced before, the 药剂师考试 in the year of 2024. As we can see here, in the last row, we could see with only 7 billion, we could pass the national pharmacy examination thanks to the Huawei GPT-01 style reasoning pass. Other than the text-only medical language model, we also try to extend the Huawei GPT for multimodality scenario, especially probably we have some medical images from X-ray or CT or whatever, and we want the model directly understand such images based on a text language model. First, we have a lot of data benchmarking RHF, which was working in medical scenarios, or in general scenarios. The most important part that we want to highlight today is about our multimodality medical language model. Especially, we get the data from OCAV. Why we want to get data from OCAV? PubMed is like a preprint papers for experts. Probably such a paper may not be peer-reviewed, but the paper was quite fresh. So we collect the data from PubMed. So one philosophy for PubMed is like the data is independent for the benchmarking. In the literature, in the archive, in the previous papers, there are quite fresh information posted by the medical experts. But the benchmarking is from another data source. So we have somehow a gap between the training corpus and the benchmarking. They will be more easy to evaluate the improvement. So we take the archive or PubMed paper as the input, and we have the image probably in the paper, and we also have some inline caption or mention about the figure. And we ask one existing powerful language model, multimodality language model, for example, GPT-4, to rewrite such a caption based on the paper caption or inline mention. And then we want to ask the model a few questions based on the description. So we could get a lot of image, caption, and question answering pairs. We feed all this data to the language model, to let language model to understand the medical information in the images. This model get great success, especially in the MMLU healthy and medical track. We are ranking the second best right after GPT-4o. And also in the Hugging Face, the model get 200,000 downloading per month, which is the highest downloading models in our group. How to use such a model? We deploy an online website, but however, this website may not be able to use now because we do not have enough inference machine for that. It's like we can upload in some medical images or just images from the natural cameras, and we can ask a few questions based on the images, and the model could respond. More than the images, we also try to use Sora or video generation model to generate some video for science popularization. It's like people usually, even from the public people, they want to learn some medical information, but somehow the medical knowledge may be termed with very complicated professional terminology we may not able to understand. So if we could develop the video based on the Sora-like video generation, this will be more easy for the public audience to know everything about medical knowledges. It's good for science popularization. And we will release this model and also pipeline for medical doctors to efficiently prepare their video for science population very soon. Another work we want to show is about a speech-language model. Why we want to use speech-language model or develop speech-language model? Probably you have already tried 千问, 豆包, or ChatGPT or DeepSeek. But in some app, they probably could let people use speech to communicate. But the oldest traditional solution is developed by ASR model with a language model. ASR is for automatic speech recognition. First, transform your voice to text, and use a text-only model to deal with your instruction or prompt. But for such a paradigm, they may ignore some environment, voice, speaker information, power linguistic. Such information in most of the daily use or research or study work, they might not be important. But there are some special cases, for example, in medical scenarios, if the patient come into the doctor's office, they may have some cough. Such information will be very important for the diagnosis. How we can combine to learn this non-semantic information in speech-language model will be useful in some scenarios. Another example will be the education scenarios. Let's say you want to have a large language model for the tutor for English speaking. Probably they can correct your pronunciation. So the model could be able to perceive how you pronounce. Maybe they're wrong, but they want to know what the original sound you pronounce, and they want to correct your pronunciation. For such a model, our model is called sound wave. In that model, we use only 150 data in 千问 compared to 千问2 audio, which is a SOTA speech language model, taken nearly maybe 5 million. I forgot. It's like 5 million hours training corpora, training speech. But our model only use 150 data, but the performance in most of the speech related benchmarking, the model is better than the 千问 audio with less data but better performance. That's why we call it less is more for speech test alignment. By doing so, even the researchers in academia, university, they also probably have the computing resources to train for speech language model, especially in understanding aspect, not for generation. More than the multimodality extension, we also try Huawei GPT in multilingual scenarios. Especially, we developed a series of Arabic language model, which adapt our existing language model in Arabic languages. The 3 versions, in each time release one of the 3 Arabic language model. It was the best open source language model in Arabic. And also we got a lot of attention from Financial Times, from 环球时报. But due to the very complicated relation between Arabic China and the US, we shut down this research. But inspired by the Arabic language model, we try to extend medical language model to a broader audience, especially the Apollo 1, which works for 6 languages, which could use medical language model to be publicly accessible to 6 billion people. And then another version, the reason why we want to develop multilingual medical language model is that we just simply combine the data in different languages. It could improve the performance. As we can see here, in the media group, we have 6 languages. They are training on specific languages. But if we combine the data together, which is the last row, it can not only improve the popular languages, but also could improve the medical benchmarking in low resource languages. That's why probably we think the multilingual corpora could be complementary between languages for medical scenarios. We scale our model from very smaller size. Smaller size could be easy for employment, and we also try to train a very large model. The largest one is 72 billion. And the second version, or Apollo, we developed multi-language model for 50 languages, which could democratize medical language models for 8 billion people, nearly cover 95% population in the Earth. And this paper got accepted in actually year 2025, and the model is based on mixture of expert. Just one philosophy why we want to develop a MOE based model for multilingual medical language model is that the MOE, which is a sports language model, the model will automatically route to a part of the parameters during inference. For a dense model, which was in every time all the parameters are active, but in MOE we only active a part of the parameters. The reason is that there are some language-specific information in medical scenario. For example, in traditional Chinese medicine, 中医, we have our own philosophy. But if you want to use a single model to try to deal with both the Western medicine and the traditional Chinese medicine, they may have some conflict during the inference or prediction. So if we can specify part of expert to deal with a special language, probably they can capture better the cultural or cultural environment for the applications. They may avoid some kind of conflicts. Okay. More than our multilingual and the multimodality extension for medical language models, last part I want to share the application part. Especially, we developed the Huawei GPT medical triage system, which is like before you went to a hospital, probably you have to specify which department you're gonna to go. In Chinese, we call it 科室. This is quite different from the Western system, which is a GP based. This is a physician, general physician that could first talk to you and get you to a specific hospital. But in China, usually people directly went to the hospital, and probably there's a nurse sitting in the hospital, and they will ask you a few questions and get you to a specific department, 科室. And we want to try to use Huawei GPT in such a triage system. The philosophy is that if we let ChatGPT work in some clinical scenarios, for example, diagnosis or treatment, probably we have some case the model doesn't work very well. There will be some ethic or legal issue. But for triage systems, the worst case, maybe just the patient may have to pay another 25 yuan to go another department. If this not involve any urgent situation, the bad consequence is tolerance. And in such case, we develop Huawei GPT in 16 local hospitals in Longgang district. Longgang is a district in Shenzhen city, is where Huawei is located. If you are in Longgang district, you can directly go to the 公众号. Then maybe they have some demo. You can see how it works. You can talk to maybe I don't know whether we can hear anything.
我肚子有点疼，挂什么科呀？就是小肚子有点刺痛。没有其他症状。
Okay, then they give some prediction, and you click the bottom, you can go to the system to make appointment with a doctor. Everything is integrated to the local system from the hospitals. Also, our philosophy to develop a trustworthy system or is to through a new technical roadmap is we want to do a self-play between patient and doctors, and to achieve one goal is called generalist medical AI. We borrowed this idea from AGI, artificial general intelligence. In AGI, people want to develop one foundation model that could work for every applications with no domain-specific data or with limited data-specific data. The similar, we defined the GMAI, which is one medical foundation model with limited data or without task-specific data. The model could work for every downstream medical tasks. The goal is with a quite great vision. We may not implement such a GMAI in 3 years or 5 years. Probably we can work for many years. But the roadmap we want to goes to philosophies, the self-play between patient and doctor. Especially, we want to first go through one intermediate stage to do medical education to train human doctors. To train human doctors, we have to collect a lot of patient cases to prepare the evaluation criteria to get the professional feedback for the human doctors. So if we have already finished the system to train good human doctors, we could borrow such an idea to train AI doctors. That's why we have two-stage roadmap. First one, go for medical education to train human doctors, and borrow everything to train AI doctors. The connection between the two stages is that if we could train if we have a good system to train medical students or medical doctors, we could build an AI-friendly doctor community. The community could be medical students or doctors. They can provide cheaper and scalable professional feedback to our GMAI model training. This will beneficial for the whole roadmap. Okay, probably from Google or from Baichuan or from Zhifubao. There's one app called Zhixiaobao in Zhifubao. They're working for a healthy care scenario, and they probably want to scale the data and the models. But one tiny difference between general domain and the medical domain is that in medical domain, the errors is with very low tolerance. There is 1% possibility the model could produce misleading or wrong information. They will cause very bad consequence. So we have to make our model very robust, trustworthy, and transparent. For that, we needed to make every training steps, the evaluation criteria, the reasoning steps to be correct, to be transparent. So medical education probably could be an intermediate stage to prepare everything for medical scenarios. And we are very proud that in our university, the Chinese University of Hong Kong, Shenzhen, we will have the largest medical school in Shenzhen. And every student is training in English environment. So the system could be easily connect to not only the Western system, also the Chinese systems. They will be an ideal place for us to explore the GMAI. Here's one example how we train the human doctors. We use AI-powered. It's like we want to build a patient case, and they can have some different kind of body checking information, the voice from the patient, and also they have some video generation to let the trained doctor more aligned with the real scenarios. So everything is synthesized by video generation model, audio generation model, and large language models. And we want to provide enough hints and also evaluation for the human doctors to better equip them with professional medical knowledges. Okay. Lastly, we want to also try another application, which maybe we can call it a medical search engine. In the search engine is like, first, we want to do the ARM routing. Why we want to do routing? Because the model developed very fast. We in this year after Spring Festival, the DeepSeek became very popular not only in China but also in the West terms. Maybe in a few months later, we probably have Pangu or Qianwen, any other models. So if we could develop one routing strategy, the model could route to any models. There are many reasons to do routing. First, different models, they have their own special working scenario. For example, Qianwen may be good for diagnosis, and DeepSeek may be better in the treatment. So we want to make the expertise for each model. Secondly, is the cost-effective trade-off. We have different styles of model. Let's say Qianwen, from 7 billion to 70 billion. But for an easy question, probably we can use a cheaper model. For a difficult question, probably we can use a more powerful model, which will cost more. And one more issue is about the reasoning. In some cases, we need a O1-like reasoning, but they have to take 1 to 2 minutes to get the response. But in most cases, the model may not necessary to use long reasoning, slow thinking O1 output because it's time consuming. So we're gonna trade off everything between the cost and the effectiveness. The second part is reinforced RAG. It's one algorithm we want to develop in medical scenarios. We want to output every sentence in our book is supported or driven from or given evidence. This could be trustworthy sources from like medical guidelines or Wikipedia or any information that is given by an authority organization like Wei Jianwei or NIH or whatever. And also, we want to make a medical agent. Such an agent will directly access some local systems in our hospitals. For example, if I got sick, I want to find one doctor which is close to my location, and he or she is available in this afternoon. Then we have to access the internet or the system from the hospitals to check which doctor is available this afternoon. Okay, that's all I can share. Thank you. I'm ready to answer questions.
If you have any question, please raise your hands.
Check. Okay, hi, and thank you very much for the talk. And yeah, I have a question about the safety and, as you mentioned, trustworthy target. So when we are talking about medical large language models, we will always be worried about safety, right? Because if it makes mistakes, then it is about lives. So I'm pretty curious about your goal of trustworthy because it directly related to how we can achieve it and what is the result after we achieve it, right? So if your goal is to completely zero tolerance to incorrect or mistake, then maybe the current way of learning large language models will be, we need to make some change, right? So could you please share some of thoughts?
Okay. So I have one proposal for such a question. That's the confidence assessment. We will have different color for our output. For example, our response, we have 100 sentences. We will give a confidence score for every sentence. For example, the 10th sentence probably they may have hallucinations or wrong informations. We will give a warning or different color. And such color will tell you, okay, this sentence might be wrong. And they can be different kind of degree of the colors to specify the risks. And the human or the doctors or the public people, they can give some annotation. Okay, I think this sentence will be a higher confidence than the given one, or be lower confidence. So such feedback will improve the confidence assessments. So that's why that's one proposal we want to investigate to tell the users how much such a sentence level trustworthy, not the whole paragraph or response. So I think this will help a little bit.
Oh, I see. Thank you.
Any other question? Okay, thank you. Now let's welcome Ting Qiang Xu from Tsinghua University. Currently, he's a second-year undergraduate student now, and he has won IOI champion and ICPC World Finals gold medal in his career so far. Today, his presentation topic is retrieval data structure, based on his paper accepted in SODA 2025. Welcome.
Hello, everyone. Thanks for the introduction. As Jingwang just said, I'm also a competitive programmer, and I'm younger than most of you guys, so I heard of many of your names when I just started doing competitive programming, so I'm a big fan of you. So thanks for UCAP and also Huawei for giving me this opportunity to stand in front of you to give you this talk, and also just for sharing some interesting problems, algorithms, and maybe showing that some tricks or stuffs in competitive programming can also be useful in the field of theoretical computer science. So this talk is about retrieval data structures. Many of you may haven't heard of this name before, so let's start by introducing what a retrieval data structure is. So first, we know what is a dictionary, or a more familiar name, hash tables. We have some keys come from a universe U, and for each key k belongs to k, has an associated value fk, and these values are vivid strings. And the dictionary supports the following operation. The data structure is giving a code key k, and if the key k is indeed in the key set, you need to return the associated value f of k. And if otherwise, the key is not in the key set, you need to return that the key is not in the key set, supporting the membership queries. And for retrieval, we also have these keys k, and also have the values f of k. And the key difference from dictionaries is that when we query the retrieval data structure a key, when the key is not present in the key set, the retrieval data structure can return anything. So we do not need to support membership queries, do not need to support queries such as like returning if the key is in the key set or not. So this is retrieval data structure, and for convenience, we assume that we denote the number of keys as n and the size of the universe to be a polynomial of n, and let the length of the values v be O log n. So what are retrieval data structures for? Because retrieval data structures are weaker than dictionaries, but its space consumption is like smaller than the dictionaries. It can use a smaller number of bits to store, so it has many real-world applications. So first of all, you can use the retrieval data structure to build perfect hash functions. If you only need to support queries with respect to the keys in the key set, you can use the retrieval instead of a dictionary. And also, you can use retrieval data structures to construct a data structure supporting approximate membership, approximating the probability that key is in the key set or not, and is further used to construct like filters, which is widely used in the database system and something else. And it's also useful to construct space-efficient static functions. So it has many real-world applications. So that's why we study it. So besides query, we also want to ask for different levels of dynamism in retrieval data structure. So we introduce the following natural 3 other operations. The first one is update. The data structure is giving some key k in the key set, and we update its associated value. And we have the insertions. We are giving a key currently not in the key set, and the associated value f. We add the key value pair kf into the into the retrieval data structure. And the final one is deletions. We are giving a key K in the key set and delete it from the data structure. So here comes the different variants showing the different level of dynamism of the retrieval data structure. We call a retrieval data structure static if it supports only queries, and value dynamic if it supports only queries and updates. And we call it incremental if it supports queries, updates, and insertions. And we call it dynamic if it supports all of the queries, updates, insertions, and deletions. So what's known of these settings? So first of all, regardless of the settings, any solution must use at least NV bits. So this is because you at least need to store the values of the keys. So this will cost NV bits. And if the solution uses space NV plus R for some R, then we say the data structure have redundancy R. And our goal is to determine the optimal redundancy R in these 4 different settings. And for dictionary, we have the following theorem, showing that a fully dynamic dictionary can be constructed in linear time, and it can support all operations, insertions, updates, deletions, and queries in OK time, costing NV plus log U choose N plus ON log K times N. So this means there are K times log. And so NV is the number of bits we used to store the values, and log U choose N is the number of bits necessarily to store the information about the key set, because you can do membership queries to query all of the keys to the dictionary, then you can recover the whole key set. So the entropy shows that log U choose N is the smallest number of bits you can use to construct the dictionary, and we can regard it as constant time and ON redundancy, because any constant number of logs N is really small, and in most of the cases we can regard it as just ON. So this is a well-developed result for dictionaries, but what about the retrieval data structure? So this table shows the lower and upper bounds of all 4 settings of retrieval data structure. So first, for static case, the lower bound is 0. This means that you can use we do not know if one can prove that you at least need some NV plus something. But there's a very simple algorithm that uses only NV bits. That is, you can just interpolate a polynomial, and such that if you evaluate the polynomial on a key k, the polynomial will get the associated value f of k. So this polynomial has degree n minus 1, so it has n different coefficients, and each coefficient will have almost v bits, so this will only cost nv bits. And so now we mainly focus on the case where all the operations can be handled in constant time. So there is a upper bound of little on that supports operations in constant time. This is followed by a sequence of work. And for value dynamic case, the lower bound and the upper bound is both n. So the redundancy is tight and is linear. And for the incremental and dynamic case, the redundancy is larger. First, let's look at the dynamic case. The redundancy is bound to be n log n. And the incremental case, the redundancy is n log n over v. So this is a very interesting bound. It says that if v is exactly log n, so then the incremental case has redundancy on. So it's linear and is equal to the case in the value dynamic case. And if the v is like log to the 0.99n, so log n over v becomes log to the 0.01n. So this term becomes n log n, which is equal to the dynamic case. So this shows a phase transition when the value of size decreases. So in this talk, I will kind of go through the algorithm for the dynamic and the incremental case. And I'm showing that, so this algorithm I think is pretty interesting and has many like tricks we used to do in the competitive programming. So let's first talk about the easier case, the dynamic one. So we need to store some information about this set K because we need to support insertions, updates, and deletions. So there needs to be more redundancy. than the static, than the polynomial interpolation methods that we just introduced. So for dictionaries, the number of bits is log u choose n. So we assume that u is a polynomial of n, so this is n log n bits. And here we only need n log n. So now I will show how to do this. First, we define a threshold L equals to log n plus O log n. And we define a global hash function H1 that maps the universe U to a smaller universe of size 2 to the L. Here 2 to the L is n polylog n. So we maintain a dictionary with universe of size 2 to the L. And when we have an insertion kf, we just insert h1 of kf, the key value pair, into the dictionary. So what we are doing here is we reduce the universe size, because we know that the smaller the universe size is, the smaller the number of bits we need to store the dictionary. So we just reduce the universe size and just regard each key, k, as h1 of k. So this reduces the information. But it comes with a cost, right? We reduce the universe size, but we cannot ensure that for all keys k, h1 of k is like distinct. So there may be collisions, and if the insertion collides with some other key, we store k and f, the key value pair, explicitly. So there are two things to analyze. One is the size of the dictionary, and the other one is the size of the collision set. So I will first explain how a query works. So this is easy because we first check if we store the key explicitly. If this is the case, then we can just print its associated value. If not, we can compute h1 of k and then query the dictionary. So this ensures that if the key is indeed in the key set, we query the dictionary and we can get the correct value. And updates or deletions are similar. I will just skip it. So for dictionary, the redundancy is the log 2 to the L choose n, because the result we have shown before. And this is, we know that log n choose m is about m times log n over m. So this is like n times log 2 to the L over n. And 2 to the L over n is, 2 to the L is n polylog. So 2 to the L over n is just polylog. So log polylog is just log log n. So this is n log log n. And the probability of collision, if we regard the hash function as a totally random hash function, the probability of collision is the number of keys n divided by the size of the universe 2 to the L. So this is 1 over polylog n. So the number of keys that collides with some other keys is at most n over log squared n, because the number of keys n times the probability of collision. So each key will cost log n bits of space storing the keys k and the associated value v. So the collision set will cost only n bits. So the total redundancy is just the dictionary, just the size of the dictionary, which is n log log n. And this is dynamic retrieval. So am I being clear? Do you have a question?
I just have like a high-level question. It looks like this construction can support membership queries. So what about it like is able to break the dictionary lower bound?
Oh, so why this does not support membership queries is that you compute h1 of k, but this maybe collides with some other key k prime in the key set, but h1 of k is equal to h1 of k prime. So when you query k, you get the associated value of the k prime. So you cannot support membership queries.
I see. Thank you.
So let's move on to incremental retrieval. So recall that we claimed that there is an incremental retrieval data structure using nv plus log n over v bits of space and allowing constant time operations. But this is quite complicated, and I will first show the simplified version. That is when v equals to log n, there is an incremental retrieval data structure using NV plus ON bits. So I will first show the intuition about why the V is like making a difference here. So we suppose the target size of our data structure is S bits, where S is NV plus ON. And so this is our memory. And at some point in time, we have only inserted the first M key value pairs. So MV bits are used to store the values. But this leaves S minus MV over M bits of extra space per key that we can use. So our key idea is to use this extra space per key to store the early keys more efficiently. Then we can delete the extra bits per key whenever we hit the space limit. So this is the key idea. And to be more explicitly, we hash keys to progressively smaller sizes and store in a table and store collisions explicitly. So progressively smaller sizes, because the smaller the universe size is, the smaller the number of bits we used to store the dictionary. So we first use the same threshold L equals to log n plus 2 log n. But with this universe size 2 to the L, we can only afford to insert the first n minus like 20 n log n over log n keys. So this is because each key will cost about v plus log 2 to the L over n. So v is the value size, and log 2 to the L over n is the redundancy caused by the dictionary. So if we multiplied n minus 20 n log n over log n by v plus log 2 to the L over n. So nv is nv. And n times log 2 to the L over n. So 2 to the L over n is again polylog n. So this is like O n log n. And minus 2 log n over log n times v is minus 20 log n. And we assume that this is larger than the O n log n before. So we can afford to insert this number of keys. And the number of collisions is the same as before in the dynamic case, which is n over log squared. So far, we are all good. We use only like NV plus ON bits. But the problem is that we cannot continue inserting elements with this hash function h1, as otherwise the dictionary will take up too much space. So this is the problem. So to deal with this, the key idea is we rehash the elements in the table to an even smaller universe size. Because when the universe size becomes smaller, the space of the dictionary becomes also smaller. So we want to rehash these elements. But we also want to rehash the elements in a way that it introduces no new collisions. So we design a new hash function, h2, that maps from the universe of size 2 to the L to a new universe of size 2 to the L2. And then we put key value pairs h2 of h1 of kf instead of h1 of kf into the new dictionary with universe size 2 to the L2. So this is good, but h2 is not just a random hash function because we want to introduce no collisions. So we need to store the description of h2. And we want to use random hash functions. So a random hash function is good with probability at least this, because like one key is collides with some other key with probability n over 2 to the L2, because n is, again, the number of keys, and 2 to the L2 is the size of the new universe. So 1 minus this number is the probability that it's introduced no collisions, and there are n keys. So by simple inequalities, the probability is at least exponential of minus n squared over 2 to the L2. So in expectation, we just like list an infinite number of random hash functions in a sequence, and we find the first index of the hash function. We find the first hash function that introduces no collisions, and we just store the index of it. So in expectation, the first hash function will occur at about like the exponential of n squared over 2 to the L2 hash functions. So the length of the index is about n squared over 2 to the L2. So again, if L is about log n plus log n, then this is n over polylog n. So H2 requires only this number of bits to store, and we let L2 equals to log n plus 2 log 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 n. And we know that round 1 has n minus 20 log log n over log n insertions. So round 2 has another 20 n log log n over log n minus 20 n log 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 n over log n insertions. Because the universe size is smaller, so we can afford new keys to be inserted. So, but at what cost? The collision probability becomes larger. But the fewer elements will be inserted. So the collision probability becomes n over 2 to the L2, which is like 1 over log log n squared. So the number of collisions becomes n over log n log log n. Because the number of keys we insert is like n log log n over log n divided by log log n squared. One log log n canceled out, and there remains another log log n in the denominator. So this is the number of collisions. So the number of bits we used to store these collisions is also small. So we do this process again and again. Like we let L3 equals log n plus 2 log 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 n, and insert this number of keys in L4, and then we have log star n runs in total. And finally, we have n over log n keys are remain, because like 20 n log 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 n is just 20 n over log n. So these keys are remain, and we put all of them into the collision set. This is all good. So in summary, we just, in the ith run, we insert elements using a hash function, which maps to a smaller universe size, but we insert fewer elements. And after each run, we do the universe reduction, reduce the universe, and without creating any collisions. And we also need to store the description of this new hash function. And anytime there is a collision, we store the original key in the collision set. So some space we need to analyze is that first, the dictionary has a very small size because we only insert that many of elements, and the description of hash functions is like n over log squared plus n over log log plus n over log log log. So by taking summation of this is also O(n). And the collision set is also n over log plus n over log log plus n over log log log. By taking the summation is also linear. So this is like the brief introduction of the first incremental retrieval data structure algorithm. And any questions? So.
Can you please return to the slide where you choose a hash function which does not create new collisions when you go to the smaller universe?
So you mean how we choose the hash function?
Yeah, maybe I missed it, but you require like a lot of bits to store the information about this hash function.
Yeah,
so you cannot just like literally go through the hash functions and choose the first one which is correct, because it will take a long time. How
so this takes a long time, but for the space analysis is correct. So I will talk about later about the time efficiency.
Oh, okay. Thanks.
So next we will improve the time efficiency of the universe reducing hash functions. So this is highly related to like what we call methods of 4 Russians about bucketing. So we partition the universe into n over b buckets for b equals to log log n to the 10th. And now each bucket has a very small universe size, because the whole universe size is like when L is log n plus log log n, the universe size is n log squared. But now, because we have n over b buckets, each bucket will have universe size of b log squared. So this is the small universe size. And we assume that the number of keys in each bucket is 4b, because if there comes a key and the number of keys in this bucket is already 4b, we just put it into the collision set. I will skip the proof of it, but this is this turns out to be okay. And because we know that each bucket has a really small universe size of polylog n, and the number of keys is 4b, which is log log n, polylog log n. So the possible number of key sets is log n to the O polylog log n is exponential of polylog log n. So this is really small and it's sublinear, and we can afford a hash table mapping from all kinds of key sets to anything we want. So we can use a universe reducing hash function in each bucket. But we still need to know that how many hash functions do we need. Since all buckets are equivalent, we try to find a set of universe reducing hash functions that works for all key sets of size 4b. So you just have these hash functions, and for each bucket, you specify an index of a hash function. And then you will use this index to do the universe reduction. And for a fixed set of 4b keys, a random hash function from this to this will map the keys to distinct elements with this property. I'll skip the detailed calculation, but we can just store like exponential of like OB over 2 to the L prime minus log n such functions, and then we will cover all these key sets. So I will skip the detailed calculation, but it turns out that the bit length of the index is OB over 2 to the L prime minus log n, where L prime is the goal of the universe reduction. We want to reduce the universe to size 2 to the L prime. And now the space usage of universe reducing hash function is same as before. We have n over b buckets. Each bucket have these sides, so in total is also n over 2 to the L prime minus log n. And the number of hash function we use is also small, because like b over 2 to the L prime minus log n is also polylog log n. So the number of hash function we used is also exponential of polylog log n. So we can afford to store a lookup table that maps from every key set to the corresponding index. And we can also afford a lookup table that takes in an index of a hash function and the input, and then map to its output. So this can be done all by lookup tables. Do you have a question?
So, how do in the bucketing of the universe, how to ensure that in each bucket there is not too much of the keys? Why is all of them cannot end up in one bucket of the universe?
So sorry, can you say it again?
Like, you have some set of keys, and you have the universe, and you do the bucketing on what? On the universe?
Yeah, on the universe. We split the universe into like n over b equal sized part.
And how, like, it sounds like kind of hash in itself, because you split the universe into the like number of the bucket, which is kind of a hashing. So how do you ensure that all the keys are not in one bucket? Like,
so we use the first hash function h1 to determine which bucket the key belongs to, and then for any universe reduction, we reduce the universe of each bucket. So if the key is in that bucket, it still remains in that bucket after the universe reduction. So we just reduce the size of the bucket universe. And means that if currently the universe size of a bucket is b times 2 to the L over log n, we do a universe reduction on this bucket, and it will reduce to size of b times 2 to the L prime minus log n. So we do universe reduction on each bucket, and it turns out that this is equivalent to do a universe reduction on the whole universe. Is it clear?
okay, when you do a universe reduction on one bucket, you want to maintain some properties that the keys, hashes of the keys that end up in this bucket, when you take the universe reduction again, they would not collide. And what is the number of the keys that ended up in one bucket? How do you estimate it?
Yeah, it's 4b, because I skipped the proof of it, because if there comes a key and the bucket has already 4b keys, we just insert the new key into the collision set. So the space cost from these keys is small.
And do you have an estimation for the collision set here?
So just storing the key and values explicitly for those keys. So we maintain that each bucket has at most 4 B keys.
Okay, thanks.
Oh. So we can store these universe-reducing hash functions efficiently and finding them efficiently. So we can do insertions, updates, and queries in constant time because we can evaluate the hash functions in constant time by lookup tables. And the universe reduction will cost linear time because we need to rehash the keys and rebuild the dictionary. So the total time usage is n log star. To improve it to linear time, it will use some additional advanced techniques, and I will not introduce the details here. So this is the retrieval data structures. So what happens when v is smaller than log n? So the insert key in each round will be n minus 20 log n over v, instead of the denominator changes from log n to v, because we cost v plus o log n bits per key in the first round. So the denominator should become v. And the final n over v keys will need n log n over v bits to store, because they have to be treated as collisions. Because in the final round, the size of the universe becomes just n, so on. So the probability of collision is constant. So you need a constant fraction of those keys to be stored in the collision set. So this is the problem. And recall, and so this comes with the number of collisions. So this is essentially the number of collisions is too large. So in the jth round, we have the first term is the number of keys we inserted during the jth round. It's n log j times n over v. And the second term is the probability of collision, which is 1 over log j times n squared. And the final log n is the number of bits we need to use to store the keys and values. So this is n log n over v log to the j times n. So we need to stop the universe reduction when log to the j times n is log n over v. And then instead of doing another universe reduction, we insert all the remaining keys into the current dictionary. So we do not do universe reduction again. We accept the fact that we need to use more bits of space. So we just insert them into the current dictionary. And the final universe size is 2 to the lj. And so the final space cost of the dictionary is just log 2 to the lj choose to n, which is the space we just mentioned. So this is how the phase transition occurs and how it works. So this is the incremental data structure. And so we have these phase transitions. As the value sizes increase, the redundancy of the data structure decreases. So actually, it turns out that this phase transition is necessary because of the lower bound. So there is a strict separation between the incremental and dynamic cases. So I will talk a little about the lower bound for incremental retrieval data structures. I will not explain all of the details, but I will show the intuition and something about lower bound. So the lower bound of the dictionary is clearly nv plus log u choose n, which is o n log n, because we can recover the whole key set from the data structure by just querying all the keys from the universe to the data structure. But after querying all the keys, we can recover the values and the key set. For retrieval, we can also try to recover the key set from the data structure. But we need some additional information about the key. So if we can prove that the bit length of the additional information is small, combined with the fact that the entropy of the key set is large, we can prove that the length of the data structure needs to be at least that large. So the intuition follows from the upper bound construction of the upper bound algorithm. So recall that the problem actually occurs at the last n over v bits, when v is smaller than log n. So we assume that the data structure occupies s bits before the last n over v keys. So if s is small, then you cannot be sure about the key set. So you may return actual values even when the current key is not in the key set. So you cannot, for example, in the dynamic retrieval, if you occurred another key k prime, which is not in the key set, but it collides with some key k actually in the key set. That is h1 of k prime is equal to h1 of k. So you return the actual value associated to k instead of the membership purist saying that the k prime is actually not in the key set. So there may cause some confusion because the S is small. You have to accept these things. So inserting the last n over v keys may lead to collisions and then cannot be handled correctly. So the setup is that we insert the first n minus n over v keys to the retrieval data structure, and then we insert the final n over v keys into the data structure. And we use them to prove that for many keys that you ask, the data structure must return that this key is in the first n minus n over v keys. So this will make that recovering the final n over v keys easier. But I will not talk about all of the details. And improving the lower bound for the dynamic retrieval data structure is also similar. You just like inserting n keys and then deleting n over 2 keys and then inserting another set of n over 2 keys. And this is something about the lower bound. And there are left some open problems. So the first is that what happens if the number of keys to be inserted is unknown? So this is an open question left by DMPP06. And this was whether one can support dynamic resizing, meaning that the space bound on the data structure depends on the current size of the key set, instead of a fixed upper bound of the size. So we want the data structure to be costing NV plus like some redundancy bits at any moment when the data structure contains n keys. So to the best of our knowledge, this resizing question remains completely open in both the dynamic and incremental cases. And for the incremental setting, one further question is whether resizable retrieval exhibits the same type of phase transition in the current result. So note that the incremental algorithm heavily relies on the fixed upper bound n on the number of keys because we need to know the number of keys n in advance. So this cannot be directly extended to support dynamic resizing. And the other one is practical algorithms for retrieval data structures. The open problem is that can we design a dynamic retrieval data structures that can be efficiently implemented for practical applications? So for the algorithm we just mentioned, so the threshold L and the dictionary used to store them is kind of not so simple. So despite the theoretical progress on the retrieval data structures, there have not yet been any practical implementations of dynamic retrieval. So it seems like that the known algorithms are not simple enough to be efficient in practice. So if one could make dynamic retrieval practical, it is likely that it will find many applications to real-world and space-efficient data structure design. So this is my talk. Thanks for listening.
Thank you so much. We ask one more question. If anybody want to ask a question, please raise your hands. Okay, then thank you very much. Thank you, Ting-Qiang. Now, oh, he's already up there. Let's welcome Mr. Rui Ji from Peking University. He's currently a fifth-year PhD student in the Programming Language Lab at Peking University, advised by Professor Zhenjiang Hu and Professor Yingfei Xiong. He's interested in program synthesis and all related programs, like program optimization and verification. In his CP career, he has won the third-place gold medal in ICPC World Finals, along with several regional champions. Now he's still engaging in relevant activities. He's the founder and the first president of PKU Student Algorithm Association. Today, his presentation topic is an introduction to symbolic program synthesis. Welcome.
Yeah, and check. Okay, so thank you very much for the introduction. My name is Rui from Peking University, and yeah, I'm very excited to share something about my research here because it is a pretty unique experience because most of you are my friends, my idols, and even my competitors when I was doing competitive programming. So thank Huawei and UCAP gave me this chance to give this talk. Okay, a very brief self-introduction. I was active in competitive programming about 7 and 8 years ago. I participated in World Finals 2017 and 2018 on behalf of Peking University. And I also have a Codeforces account, although it has been inactive for a really long time. But I'm very proud that my rating is still higher than OpenAI's model. So, and I hope, yeah, it can be higher for still for a long time. Yeah, and some of you may have ever read this post about segmentary beats. Yeah, this is my first project related to research I have done when I was in high school. So in the recent 5 years, I started my PhD at Peking University and mainly working on the theory of programming language, working on problems like program synthesis and related topics, including optimizations and verification. Yeah, I know all of these topics may be pretty far away from competitive programming. So today I'm going to give a very brief introduction about the key ideas and the key spirits of program synthesis. Okay, so the first question, what is program synthesis? In just one sentence, the goal of program synthesis is to generate a program that satisfies some given requirements. For example, the most simple form of requirement is input-output examples, right? So suppose that the user provides some input-output examples like this, then the expected result of program synthesis would be this program. It is a maximum program takes 2 integers as input and returns a higher integer between them. Yeah, okay, so this is the most basic case of program synthesis, but because we have many different kinds of programs, many different kinds of requirements. So actually, program synthesis have a very broad content. For example, we can use program synthesis to do optimization. This is a program that computes the sign of an integer, right? So it returns -1 when the integer is negative, returns 0 when the integer is 0, and returns 1 if it is positive. Yeah, but we know that although this program is correct and straightforward, we know that nested ifs and else is not so friendly for CPUs, right? We need to do a branch prediction and do some other things. So if we want to get a more efficient program, a natural idea is that whether we can rewrite this program using only low-level and more efficient operators. So this also forms an instance of program synthesis, and the expected program here should be this program, right? Where we replace all if and else with lower level operators. And such kind of optimizations happens frequently in modern compilers. Oh, sure. Yeah, this is 2 times of taking bitwise NOT. So yeah, the first one will take turn 0 to 1 and other integers to 0, and the second will reverse. So it will change 0 to 0 and other integers to 1. Yeah. Okay, and also program synthesis can help us do some software engineering things, right? For example, this is called in a game, Hearthstone. And we know that programmers in Blizzard are really good at producing bugs, at least much better than writing programs, right? So if we can just kick them away and use a program synthesizer to write these programs, then Hearthstone will be a much better game than now. Yeah, and also, of course, all of us are players in competitive programming. So, of course, we'll be interested in solving problems in, for example, ICPC World Finals, right? So this is also an instance of program synthesis where our goal is to write a program that is efficient and use few memory and also satisfy the statement. So if we can solve it automatically, then maybe we can automatically win the ICPC World Finals. Yeah. Okay, so all of these are instances of program synthesis. And as you can see, for the last two examples where we try to doing something with natural language, then it will fall into a very standard program generation problem, right? So when talking about program generation, one thing we cannot ignore is the modern large language models. So they can really, now they can do many very interesting things, many amazing jobs, and also OpenAI has claimed that their model has achieved a higher and higher rating in code forces from GPT-4o to 03. Yeah, but I will not talk about this today because I know you have heard large language models many, many times these days, right? So I will talk about something different. So from a high level, a large language model falls into a branch of artificial intelligence, which we call it connectionism. Yeah, this word is from connection, so it is very intuitive. That is, we build a very huge neural network by connection, and then try to using some machine learning techniques to find a good neural network. Yeah, and today I'm going to talk about another branch of artificial intelligence, which is symbolism, and this word comes from symbol. Okay, now here is a very difficult problem to me, is that how to give a very quick introduction to the key spirit of symbolism, because symbol is a very abstract thing. And I try to ask this question to DeepSeek R1, but the problem is very abstract and is not satisfactory. So I have a good idea that given that all of us are very like competitive programming, maybe I can start with a warm-up problem and then gradually introduce the key idea of symbolism. Okay, so I have prepared a problem, which is a real problem for a Chinese competition, official competition, which is NIP Junior Group in about 15 years ago. And this problem is very easy. I asked my friend, and all of them told me that it is only in a level of D1A. And Tingqiang, our previous presenter, solves this problem successfully in 10 seconds. So to make the things more interesting and more challenging, I will add an extra limitation that I will totally hide the statement of this problem from you. Instead, I will only show you 4 improper examples of this problem, and let's try whether we can discover and recover a correct program from these examples. So for example, this is the first improper example. So the input of this problem is the symmetric matrix where nothing appears in the main diagonal, and its output comprises 2 lines. The first line is a string. For example, here the string is Alice Wing. And the second line is an integer selected from the matrix. Yeah, and I marked the original place of this integer as red. Okay, and here are the remaining 4 improper examples. Yeah, and next I will play a fragment of music about 2.5 minutes. And if you are interested in this problem, you can take this time to think. And if not, you can just enjoy the music and have a rest. Yeah, so hope you enjoy the music and have some interesting observations. So let's now move back to the talk. Now I'm going to review the answer of this problem. So let's make some interaction. So every time when I show a true observation, so please raise your hand if you find it as well, okay? So the first observation is that for the first line is always Alice win. Can you find it? Okay, excellent. All of you, most of you can find it. Great. Yeah, and yeah, I think this observation is pretty intuitive, right? Because for all of these 4 examples, the first line is always Alice win. And the second line is more challenging, and its rule or pattern is also more complicated. So the second line is always the maximum value among the second maximum in each row, or equivalently, it is the maximum among all values that are not the local maximum in their column and row. So anyone find it? Okay, much fewer people. Yeah, excellent job. Yeah, but don't be frustrated if you cannot find it, because it is actually very challenging problem, and O3 Mini cannot solve it at all. O3 Mini will give me a pretty complicated observation that try to connect the result with a standard approximation of the TSP problem. So to be honest, I kind of believe this result when I first see this, because this is just 4 examples, right? So I spent about 5 minutes to find out with some papers and pens and calculate for these later 2 examples. But yeah, it is totally nonsense. Yeah, anyone find the same, have the same result as O3 Mini? Please raise your hand. Okay, yeah, all of you are much better than O3 Mini. Good job. Okay, so from this warm-up problem, I want to introduce the concept of inductive reasoning, yeah, which is a very important part in how humans make doing inference and think about some things. So the input of inductive reasoning sometimes starts from some observations or some data, or just like input of examples in my previous slide. And when doing induction, we try to guess some conclusions and recognize some patterns and try to generalize it into some more abstract and more general conclusions. For example, such kind of thinking is very important in discovering some physical laws or some scientific results, right? For example, Newton has an observation that the apple fell down from the tree. Then he made some generalization and finally gets the law of gravity. Yeah, okay, so given the importance of doing inductive reasoning, and yeah, as you just filled through the previous, our warm-up problem, actually for human, it is very challenging to do inductive reasoning, right? And our results may not be so reliable. So for example, for me, while I was in World Final 2017, I got a totally incorrect conclusion for a problem and make my teammates really mad at me. And also, yeah, and I think fundamentally there are 2 challenges for human to be bad at doing induction. So the first is that our human brain can hardly deal with large scale of data, right? For example, imagine that in the warm-up problem, I did not give you metrics of size 4 and 6, but I give you a matrix of size 100, then this problem will be impossible for just 2 minutes, right? And on the other hand, humans sometimes will be affected by our prior knowledge and our education, or or other talks, or others' opinions. So for example, a very old example is that when people in tens of centuries before, when they see that the sun rises from the east and set to the west, then they summarize using the induction to get the geocentric model, right? They will naturally put Earth at the center and suppose that the sun will rotate around the Earth. Yeah, and after that, when more and more orbits are observed, then people will not try to challenge this model. Instead, they will try to add more and more complicated observations to the original model, and we will get things more and more complicated. But we will tend to ignore a very simple truth, which is different from the scratch. Okay, so hope you can agree with my claim that human is not good at induction. So if you agree with that, then a very natural idea is that how to design a reliable artificial intelligence that can help us to do induction, right? Help us discover some useful laws, maybe physical laws, or solving some problems in competitive programming. Okay, so for example, back to the warm-up problem, then the problem here is how to design an inductive program synthesizer that can inductively find a program solves these examples from only these examples. Okay, so let's think about what properties should a good inductive program synthesizer satisfy. For example, we don't want O3 to be such a synthesizer, right? Because it can possibly give us some totally incorrect conclusion, even violates these given improper examples. So we would be interested into such a property. We call it soundness, or you can understand as correctness. That is, such a synthesizer should guarantee that its result always satisfies the truth or the observations we give it. However, just the soundness is not enough. Just in the geometric case, right? We can always overfeed some examples by adding more and more patches. For example, when first seeing the first example, we can just write a program directly put to the output. And of course, this program will fail on the second example, but we can add a very simple patch to distinguish these two integers. And also, we can do it again and again and again, so that we can always easily get a program satisfying all improper examples. But clearly, it is not what we want, right? So we need another property, which we call it completeness, or it is close to generalization. So we want this approach to ensure that we can finally find the target program we want after a finite number of iterations, or given a finite number of observations. Okay, so with all of these introductions and pre-cases, I think I'm now ready to introduce you the key spirit of symbolism. So what is symbolism? Just my personal understanding is that we put these properties always at the first place, even with a higher priority than the performance. So a symbolic approach will always ensure both the soundness and the correctness, and only when some observations, only when some optimizations or some techniques will not affect these two properties, we will incorporate it into our system to improve the performance. So in this figure, the developer of a symbolic approach is building bottom-up, right? So first with the guarantee, and then with better and better performance. And instead, compared with the approach in, for example, neural networks, there is a very clear difference in foundation, right? So because the spirit of connectionism is try to use a neural network to feed some data, so they will naturally put performance as the first place, and then maybe with a higher and higher performance, they will somehow achieve some empirically good performance, but they will never guarantee these properties. Okay, so this is the first part of my talk, and I think, and I hope I succeed in introducing you the key spirit of symbolism. And the next part, I will introduce you the key ideas and the key approaches in designing a modern symbolic synthesizer. Okay, so let's start. You may feel that the two properties, soundness and completeness, are pretty scary, right? For you, because maybe you have heard that it is fundamentally challenging for neural networks to ensure soundness or ensure completeness. But actually, it is very simple for a symbolic synthesizer. We can very trivially achieve it. So for example, suppose we are going to synthesize Python programs. We can just enumerate all possible Python programs as strings, just from short to longer. For example, we can just start with strings with just one chair, and then interpret it as Python programs and check whether it satisfies all improper examples. If it satisfies, then we return it as the answer, and if not, we just reject it and turn into the next program. And we can repeat this procedure to longer and longer programs until we finally find a program we want. For example, this is a Python program computes the maximum among the second largest integers in a matrix. Okay, so this is very trivial, but it works, right? So we can check whether it satisfies the two properties we want. For soundness, we will always return a program after verifying it, so the result must be correct. And for completeness, because we will enumerate all Python programs, so after a finite time of enumeration, we can visit any program we want. So, but this trivial approach also has its own problem, right? It has some significant time issue or efficiency issue. So for example, this program contains 72 chars, and if we consider all possible 256 possible choices of chars, then it will result in a very large number of shorter programs, right? So before finding this program, we have to enumerate all of these shorter programs, and the time cost would be, very huge. Okay, so how to improve it? Well, so let us consider why this general program is not. So why this general language Python is not so good at enumeration? So I think the true reason is that it is too general for general programming, and it will introduce many, the programs we don't care. So for example, to get this program, the program we want, we may visit a program that prints hello world, visit a program that prints its source code itself, and so on. But if we already know our goal is to pick up some value from a matrix, then the first two integers will be nonsense, right? Okay, so based on this observation, I think a key idea is to try to introduce some human bias or human expert to this expertise to this enumeration procedure. So a very popular idea in the study of programming language is that sometimes for a certain application domain, we can develop a domain-specific language that contains all programs we are interested in this domain, and exclude those programs we are not interested in. So for example, if we are consider a domain that only care about operating lists, then we can develop a domain-specific language including only 6 list-related operators, and we use the enumeration approach to only enumerate programs using these operators. Then there will be 2 advantages, right? So the first advantage is that there will no longer any programs outside this domain. So the enumeration approach will not visit the hello world program or the program print itself. And on the other hand, because these domain-specific operators encode some domain knowledge, it would be much easier to write a program we want. For example, here with these more concrete operators, then we can write the program we want using only 5 operators. So there will be very few programs smaller than this program, and we can easily get it by enumeration. Okay, so this approach, although looks pretty stupid, right? It is totally artificial. But it has achieved a very huge success in about 14 years ago by Microsoft. So in that year, Microsoft released a tool, namely FlashFill, for completing Excel spreadsheets. So suppose that we have a spreadsheet where the first column includes many emails. And what we want to do is extract out the name from these emails. For example, in the first line, we want to extract Nancy Freehaver from this email. Okay, now suppose that we go back to 2011. Then note that in that year, there is no large language models, there is even no deep learning models, and most people have no knowledge and experience in programming. So what they can do is just to write these names one by one, just by hand. So at that year, there are millions of people struggling in fighting with spreadsheets, and many people just have a full-time job in dealing with spreadsheets. Okay, so how FlashFill can help this procedure? When the user started to fill this spreadsheet, it will trace the procedure and extract all those finished lines as input output examples. For now here, the user have already finished the first line so that we get an input output example. And then it will use a symbolic synthesizer to synthesize a string-specific program in a well-designed string-specific language. And then after synthesizing this program, it will apply back this program to the original spreadsheet, and by running this program on all the other emails, and then fill the result to the name column. Okay, so it has achieved a very, this is a true breakthrough approach in that year, because in that year there's no deep learning approach, right? So it is actually the state of the art of artificial intelligence in that year, and also similarly, it makes thousands and even more people lose their job and lead to many changes to the society. Okay, so this is about the key idea of symbolic approach, right? So if we can just get the properties by naive enumeration, and if we want to improve the performance, we can try to manually introduce some domain knowledge by design a good domain-specific language. Okay, but of course, this procedure is not so satisfactory because it needs an expert, and it will be pretty challenging to design a good language. So a natural question here is that, can we automatically learn a domain-specific language? So the answer is true. So we also have our own learning algorithm for symbolic approach. It is called library learning. Just like many other machine learning approaches, we also need a set of training set and a basic model. And here, this is a basic language which includes some, it can be pretty general and includes some basic constructs. Then what we will do is to first run a synthesizer to try to solve these tasks using the naive language. And because the initial language can be very general, so we can only solve some easy problems. For example, a very basic expressions for operating integers. And then the most important part, in the learning part, we will try to extract out those commonly used subprograms as new library. For example, here we find that the operator 2 times is used twice. Right? So we may introduce an operator called double, which just abstracts this operator into one operator. Yeah, and then we will add this library back to the base language, and in this way, we will make the base language more and more specific, and in the next iteration, we are supposed to solve more difficult problems, and then we can learn more specific libraries in the next iteration. Okay, so this approach has achieved success in many different domains. For example, 4 years ago, there's a work trying to use library learning to discover some physical laws. So they start just from a very general language, including only very basic operators of lists and float arithmetic operators. And then during the library learning, it will first learn many operators related to vectors, and also have some, summation operator. And as the library learning goes step by step, it can learn more and more complicated programs, such as dot product and some operators related to period. And after doing it for a long enough time, it can discover physical laws, so many well-known physical laws, right, such as the Newton's second law and also the Coulomb's law. And with the learned library, it will be pretty simple to express these laws. But if we use only the original expression, then the cost will be intolerable. The program will be too large for a basic enumeration. Okay, so this is everything about I want to talk about symbolic approach. So all of them are pretty old techniques, and now the era has changed, right? So today it is the era of large angle models, and where the performance of connectionism has improved greatly and can achieve success in many different domains. Yeah, so it also forces research in symbolic area to make some changes. Yeah, but as I have introduced before, in foundations, these two approaches are pretty different, right? So symbolic approach can ensure some properties we are interested in, and for example, large angle models here have some very good performance. So this is actually a pretty good thing, because we have 2 different ideas for the same problem, then we can just combine them and produce many and many garbage papers, right? So yeah, a very natural idea is that given that symbolic approach is basically an enumeration, so maybe we can just use large angle model to provide some guidance or some private knowledge for the enumeration. So in this way, we are still doing enumeration, so we still have the soundness and the completeness guarantee, but we can still enjoy the improvement led by large angle models. Yeah, and if we do so, we can find that such a combination, a guided enumeration, is actually a very perfect playground for reinforcement learning. For example, because we are doing enumeration, so we have a very clear search stage, and we are making decisions in this search space step by step, right? Have a very clear space of decisions. And also we have a very clear definition of reward, because the symbolic approach can ensure the correctness, because it means that it can verify whether the result is correct. So we can just assign some positive reward if is correct and assign a negative reward if it fails. So there have been some interesting work following this line, and the most famous work should be these two from DeepMind, right, recently. They are trying to use approach to solve mathematical problems. For example, for the geometry domain, they design a DSL for related tasks and also use a model to guide. And for the proof domain, they try to use some language like Cork and Leon to represent proofs and also use some models to do reinforcement learning. Okay, so how about future? So if we have, so in the previous slides, I've shown you an example of flash field, right? It is the state of the art of the artificial intelligence in about 14 years ago. And now we have large language models, right? It is the state of the art of artificial intelligence today. And if we think about the difference between them, we can actually find that the algorithm is not really important, right? For example, the gradient descent has been invented many, many years ago. So the key important part is that how much computational resource we can get, right? So imagine that in the future, what if we can easily enumerate programs with thousands or even tens of thousands of operators? Then we will be able to win ICPC World Finals very easily, right? So yeah, because most programs, most solutions to ICPC problems will not be longer than 10,000 of operators. And what if one day when we get some alien techniques that we can doing some unlimited enumeration, then maybe we can just try to enumerate proof for those big problems, right? To enumerate a proof for whether P equal to NP or whether P not equal to NP. Once the logic system underlying can express the proofs of these theorems or conjectures, and once these proofs exist, then we can ultimately find it. So I would like to call it like the scaling theorem of symbolic approach. So comparing to the scaling law of large language models, right? They are just laws from experience and observations using inductive reasoning. So the scaling of symbolic approach is actually guaranteed by its foundation, this property of soundness and completeness. So they give us a very strong belief that if the truth exists, we will be able to find it ultimately after spending more time and after spending enough time and enough resource. Okay, so this is everything I want to share, and yeah, thank you very much. Any questions?
Thank you very much. If any question, please just raise your hands. Okay, thank you very much. Now and last, let me welcome directly from Noah's Ark Lab from Huawei to give a talk. He's a senior researcher at Huawei's Noah's Ark Lab Canada, where he is a member of the decision-making and reasoning team. He has received a Master of Science degree from Alberta Machine Intelligence Institute, the University of Alberta in 2022. His current research interests include reinforcement learning, LLM reasoning, and policy-guided heuristic search, as well as their applications in Huawei's products, such as Pangu LLM. Welcome.
Thank you for the introduction, Jinbong. My name is Derek, and I'm a researcher here at Huawei's Noah's Ark. Today, I'll be presenting on behalf of Dr. Dong Li, our beloved ROHF team lead at HQ, who unfortunately couldn't be with us here today. Please bear with me, and I'll do my best to help share his wisdom with our colleagues and audience here and online. Wait. Oh. Right. So to give us some background information, the current LLM development includes 3 phases: pre-training, supervised fine-tuning, and reinforcement learning through human or AI feedback. In supervised learning, we train a model with some data set we sample, and where we apply is cross-entropy loss with backpropagation updates to obtain a calibrated model. Therefore, here the performance of the model largely relies on data collection and curation. In comparison, in reinforcement learning framework, the agent generates its own experience and obtains feedback from the environment for training instead of from a data set. So where we stand today, first, we're looking for improving the model's reasoning abilities, where we hope to incorporate deliberate thinking time mechanics in the model's response, such as some of you have attempted during the challenge the other day. And second, we hope to continuously improve the model in a product data flywheel. And finally, we would like to combine efforts in data techniques, system engineering, and algorithm development to build a better AI. So we've been watching a trend during roughly the last 2 years, where it begins with the introduction of fast-thinking LLMs, such as GPT-3 and ChatGPT, which kicks off the revolution of generative language models with instruction tuning and RLHF techniques. And then later on, the open source models, such as the Llama 2, signifies the paradigm of pre-training and post-training really starts to mature. And more recently, the release of reasoning models, such as OpenAI O1 and DeepSeek R1, has demonstrated the capabilities, the possibility of attaining long chain of thought reasoning through pure RL and rule-based reward, with a considerably less amount of training data required. So now, to give you some background, reinforcement learning is a key part of the deliberate thinking LLM training process. For example, it plays a central role in building DeepSeek R1. Essentially, it uses a rule-based reward and group relative policy optimization to first train a reasoning model. And then it generates some reasoning data with a format that contains a reasoning process and a summary, like you will see here. It then fine-tunes this long chain of thought data on the base model to further improve the potency of the RL training to attain even more impressive reasoning capabilities with the help of various rule-based reward signals, such as accuracy and language consistency reward. So together with data, it builds a really strong reasoning model. Now let's review some basic concepts in RL. So RL problems are typically framed as a Markov decision process, as we know. MDP is a quadruple, where S and A are the state and the action space. R is the reward signal. P is the transition probability, which encodes the dynamics of the MDP. It represents the conditional distribution of transitioning to state S, T+1, and emitting a reward R from state S upon taking action A. So the Markov property states that to make predictions of the behavior of a system in the future, it suffices to consider only the present state of the system and not the past history. And in addition, in practice, the true reward function and the state transition model are usually unknown. And additionally, the RL objective here is to optimize the control strategy, so AKA as learning the optimal policy, in order to maximize the cumulative reward. The difference of the difference of the value function and the action value function here is considered the advantage for taking action A. Basically, almost all RL methods involve estimating a value function, which are functions of states or state action pairs that estimates how good a state S or an action A is in order to maximize an agent's total rewards in its lifetime. In particular, the state value function denoted by V of S, here to the left, under policy pi estimates the expected total return given a state S. In addition, an action value function Q of S and A is used to estimate the expected return an agent could expect upon taking an action A in the current state S. So in a similar fashion, the policy-dependent action value function is defined as the expectation of total return taken with respect of the policy pi upon taking an action A under the transition dynamics provided by the MDP. And more specifically, so what is the reinforcement learning setting for our LLM alignment looks like? So first of all, the environment is deterministic, where the transition function is a simple concatenation of the current state and action. The LLM takes input of the prompt and predicts the next token probability distribution autoregressively, which is then decoded into a text response. And now let's go over more details here. So a typical RL paradigm for LLM alignment looks like this. So you basically have, so D here is defined as a bunch of training prompts. So you do this repeatedly. You sample n prompts from this set of prompts. And for each prompt, you collect k responses using the current model, current policy model, pi theta. And then you choose a certain loss, and then you update the model, and then rinse and repeat. So the two candidate RL loss here, the two candidate loss function here are as follows. The first is an RL loss, which is essentially a combination of reward and KL divergence that penalizes the distance between the trained model and the reference model. And the second choice is basically using the reject sampling loss. It also relies on a reward signal. But the loss here is quite simple. It's simply a weighted average of log loss among all accepted responses. And if you're a little bit confused here, we can give you a simple intuition. So intuition-wise, rejection sampling could be roughly compared with doing essentially a breadth-first search. So where we encourage the model to explore the most immediate search space supported by the accepted responses, and iteratively improve our search policy from there. Whereas we might think of when you're training using RL analysis as a parody of performing depth-first search conceptually, where we roll out to the very end to look for the final answer, essentially doing this as in the needle in a haystack problem. And then we evaluate the final answer and see if the search path is desirable, and we repeat from there. Now let's go over the RL alignment loop used in the industry. This is an orchestration of three key components: data, reward, and RL training. So there are two loops involved in this process. So an outer flywheel that utilizes the anonymized data after product launching, and there's an inner flywheel that utilizes data that mined from SFT and pre-trained data sets. So there are mainly three steps. I'll quickly go over it here, and then we'll get into more details. The first is exploration. So essentially, and it contains two smaller steps, which is query space exploration and solution space exploration. So both are used in combination to generate a diverse and difficult set of questions and solution candidates. So that is used to enrich our data. And secondly, we have an evaluation process that provides a score or reward signal to the data generation process. So we can iteratively improve our data sets and include more samples. So basically, it's kind of similar to an active learning technique. And the step three is when we basically move to training the model and then keep updating the model parameters based on some kind of loss function that we mentioned before. So we can either do this evolutionary style of learning based on RL loss based on numeric or preference feedbacks, or we can perform these updates using SFTLs. And then you essentially have a new generation of model by the very end, and then rinse and repeat. So now we'll go over each step one by one. Let's zoom in on the data space exploration. So it's basically a process of high-quality data mining and a teacher-student progressive learning framework to slowly grow the training data set. As we mentioned before, the first step is query space exploration done by the teacher model, which basically does 4 things. It gives the question, it evaluates the answer, it writes a generalized questions. So this is essentially a data augmentation process. And they also try to increase the difficulty of the question when the student could perform relatively well in answering the question. So the second part is the response-based exploration done mostly by the student model here. As I just mentioned, so it basically mostly does 3 things. It first answers the questions, and it also polishes the answer with the teacher's feedback as a helper. And here, the techniques being used includes dynamic decoding policy and tree search. So in the very end, we ended with a quite diverse and quite difficult data set to fine-tune or perform RL training on our model with. So this is great. Now let's quickly go over step 2, which is evaluation. And it includes 2 components. The first is a reward system, which we use to help provide signals to our data samples and also in training. So there are 2 types of rewards here. The first is a rule-based reward. For example, there are different types of rule-based rewards we can acquire. Like the most simple would be like just checking against the final answer. There are also different format checker, right? So these reward functions are typically good for math and code generation tasks. I'm pretty sure you guys are well familiar with this during the challenge. And the second type is the LLM-based reward. And it's basically a typical RLHF reward model you trained by fine-tuning a base model on some kind of preference data set, which we're going to go over next. So how we are basically building this preference data labeling. So you take this SFT model that does well on a particular set of tasks, and you ask us to generate a bunch of response. And you sample certain pairs. But sometimes you do it together with rejection sampling to get the ideal pair for your training. And then you basically ask either some manual creation process or a LLM as a judge system to provide a preference signal. And that's how we build the preference data set. But there's a problem here. There is inherent noise in the manual preference annotations, where the consistency between human is only about 75%. And the typical reward model we train only has accuracy about 70 to 80%. But the good news is this kind of precision surprisingly is sufficient for guiding a relatively good RL training. And the second problem is that, as we mentioned before, it's relatively difficult to obtain the true reward function in applications of RL, especially in practical problems. And in this example down below, it shows the reward function of the ETF Anemo robot. And it's quite complex. So it's composed of 10 sub-items. So it's quite hard to estimate what your true reward functions when you're in practical problems. And this is only like a simulation. And another issue is reward hacking. So this happens with using a reward model in RL training. And the core problem is the models can become outdated during the policy model's data distribution shift, and the fact that the policy model is getting updated and its parameter distribution shifts a lot from its original state. And there are the potential ways to mitigate that includes using, first of all, right, using a rule-based reward. So we no longer use so basically that is basically just getting around the problem. So we no longer use a trained reward function. We choose a rule-based reward. And that's also what DeepSeek R1 did. And the second way is to come up with diverse set of prompts so that, for example, you can use a combination of SFT data sampling and synthetic data. And that basically helps balancing out the language, so basically the general task data and the reasoning data. So basically you want to essentially have a really good coverage of the data space, and that also helps your reward model to stay on policy. And the third is response generation. So basically you want to combine some off-policy sampling with on-policy sampling, which is pretty similar to the second point. So in an experiment where we experimented a multi-hat reward model, so basically we train a reward model with not only a numeric score, but we also added another hat to predict language feedback. And what we're hoping is that it improves the precision of the reward model. And indeed, it marginally improves its accuracy as well, as you see here. Now we're going to have a quick walkthrough to explore what some key factors are in bootstrapping LLM reasoning through RL in our latest efforts in replicating DeepSeek R1. And the research questions here are, is it possible to obtain a deliberate thinking LLM with RL training and simple rule-based reward, especially on a smaller model? And the second being that, what is the gain RL can achieve compared with SFT? And the third question is that, what are the important features or patterns in the RL trained model? So for example, maybe like there could be a change of response length during the process, or there could be some kind of aha moment, like being introduced in the R1 paper, right? There's a emergence of reflection patterns. So those are the things that we look for. And the first question is, what are the key factors to train a deliberate thinking model by RL? So basically here we are considering like different empirical design choices. For example, the base model we are going to use, the RL update algorithms, the hyperparameters. And just to quickly go over the experiment setting, we use a rule-based reward, same with R1, including the format penalty and the accuracy check. And we use a mass data set, consists of, so basically like this is directly taken from the math Hendrix max data set, but we only subsample the ones that with level difficulty 3 and plus. So that gives us 8 case samples in total. And the initial policy model we tested are Q1 Mass 7B base and Q1 Mass 7B instruct. And the RL algorithm we tested include PPO and reinforce. And the testing benchmarks, we use various testing benchmarks, which is pretty standard here. So I'll skip it. And here's our first result. Based on a pre-trained model, so we can see here, RL with simple rule-based reward can significantly improve the reasoning ability. The average testing accuracy increased from initially being an average of 29.2% to 49%. So this is the blue curve. And the yellow curve is the response length that we said we are going to monitor. And interesting enough, it drops at first, what we observe is that because Q1 mass 7B base model, I guess it was pre-trained on a lot of code and mass data. So it first, initially it generates a bunch of code. So in this first phase, it essentially learns to unwind that and stops generating code. And then it gets longer again with the test accuracy during training. And we also use the same number of training data, same query with R1 response for SFT distillation as a comparison, and the average is 37.7% accuracy, which is lower than the RL performance. And next, we're going to look at some statistics of the reflection patterns in the model's response. And the typical reflection keywords we use here are try and approach, and the histogram of the keywords and accuracy basically shows two results here. The first is that SFT distill improves the performance by increasing the reflection probability, even though with useless reflections. And in comparison, RL training can improve performance significantly with much fewer reflections. So it learns to reflect at the right place. So essentially, RL only does the essential reflection it needs to get to the right answer. And during the RL training process, the number of reflection increases at first and decreases to the initial level. The RL also needs to increase reflection probability to explore better trajectory. But it generally learns to refine its reflection pattern and only use necessary reflections. Similar pattern with more recent findings also corroborates with this, that correct response is much shorter than the wrong one. So now we're showing two example questions to make the same point, where we have a qualitative comparison between the thinking patterns of three different models. The one to the left in blue is the base model, where you could spot that there's only one reflection in this question. And the second is the SFT model trained on distill data. And it basically learns pattern matching, and it does a bunch of reflections, but unfortunately it gets to the wrong answer. And in comparison, so the final checkpoint of our RL training doesn't reflect as much as the distilled model, but it gets to the right answer in the end. So here's another example. It basically shows this similar pattern. And next, let's explore the influence of initial model choice. So here we use a base model versus instruct model. And what we find is that, so here the base model learning curve is showing blue, and the instruct model learning curve is showing yellow. So interestingly, what we found is that despite learning very fast initially for when you perform a pure RL training from an instruct model, it also essentially quickly converges to relative low performance. The instruct model is rather hard to train to increase its response length, as you can see here, which unfortunately this is a desirable thinking pattern we are looking for. So this might explain the relative subpar performance we observe. So we made an educational guess here. We made an educated guess here. The potential reason might be because that instruct model has been extensively trained using the fast-thinking SFT, so basically like the short standard SFT data, vastly present in the SFT data set it uses. So, so essentially it becomes like a worse starting initial state when you perform this pure RL training. And it's hard to escape from that optima. And therefore it's hard to also escape its original response pattern. And lastly, we did some experiments with different hyperparameter settings. So we tested the sampling temperature, where we find that using higher temperature helps to generate more diverse trajectories, which leads to better performance. And the second thing we tested are how we control the learning rate throughout the training process. And what we find is that if we essentially schedule the learning rate too quickly, it might hurt the performance. There's a typo here. The model hardly changes when you measure by KL divergence between the RL policy you trained and the base model. So that's less desirable. And in summary, what we found is that RL is the key part of the LLM alignment, especially for the deliberate thinking LLM training. And second, with simple rule-based reward, RL can improve the reasoning abilities quite significantly. It is especially suitable for the task with clear rule to verify the answer. And third, data flywheel is one of the key techniques used in the industry applications, which helps to boost the performance of LLMs through iterative training. And lastly, reward hacking is an inevitable problem. So we need to use RL in well-defined tasks firstly, such as math and code first, before we are starting to exploring like using RL in other domains and tasks. Thank you, everyone.
Due to time limits, so you may communicate with our Huawei expert after the conference. So now we will thank you very much, and now we will proceed to the short tea break, and we'll play some competition reaction videos during the break, and then we will immediately start our closing ceremony. Thank you.
У меня тоже есть. Ну я... Вон, тут что-то со строками, короче, возьму. 就是 n 等于1 m 等于1是要2。不用让他那个吧。PPT 我就是行，我操，兄弟有点猛。我不懂啊。没事，你不是对不起我，这个是我都不是要跟你打。我不懂啊。再说。对。思维好，用英语学的。
afternoon, ladies and gentlemen. We welcome to the closing ceremony of the 2025 Universal Cup Finals. Please, everyone, sit in your seats, and we will start. Okay, my name is Tan Jie. It's my great honor again to be a host for today's ceremony. Before we proceed, let us take a moment to recognize Huawei. This global event would not have been possible without their support. Thank you, Huawei, for improving the future of competitive programming. Universal Cup is working on building a reasonable system to make everything sustainable. Now, please join me to welcome our co-president, Mr. Jin Bangchen, and Mr. Qing Yushi, give us a speech. Please come to the stage.
Hello. Hello. Okay, so I know that we have been very tired now, so let's be more casual on our closing ceremony. So, our dear distinguished guests and contestants, thank you for joining the 2025 Universal Cup closing ceremony. And what an amazing week we have in Dongguan. So over the past 4 days, we have experienced so many wonderful moments. We had an exciting competition, we had a challenge, and we had a city tour. We had all those, interesting night events, and those conversations, sharing the ideas and our stories with the friends from all the corners of the world. And we, the organizing team, feel truly honored to have this opportunity to connect with you, the very best ones in our community. So, in the closing ceremony, I would like to acknowledge that those staff members who dedicated their time and energy to this event. And some of them were unable to be here with us in person. They worked tirelessly alongside their studies or their jobs, and they helped to shape every aspect of our competition. And their contributions are the cornerstone of our event. They truly wish to be here, but due to some, unfrozen challenges, they were unable to join us in Dongguan. And on behalf of the entire Universal Cup team, I extend our deepest gratitude to all those who support our competition. And back to our contest, I really hope you enjoyed all the problems. So maybe they are challenging, and maybe some of them, are a bit controversial, but I hope you enjoyed all of them. So in our problem setting process, we have received 98 different problems from 60 different people with different styles and difficulty levels. And we started the process to prepare the problem set just after the semifinals in Cancun. And the scientific committee, along with other invited judges, cooperated together to set the contest. We shortlisted 20 problems in total, and we adjusted the problem set multiple times to make a balanced and interesting problem set. And to be fair, we have set many contests before, from a small school practice contest to an international championship. But this time, it's a real challenge to prepare such a problem set in such a high-level competition. And the judge team has put months of time to review every single proposal, give their feedback, and we had a lot of discussions, everyone has their own perspectives. I can remember that some authors said this problem is very easy, and the whole team cannot figure it out in a whole night. So please allow me to credit the names of all the judges. They are Li Baitian, Lou Yuchen, Xu Tingqiang, Huang Siюan, Sun Hengzhe, Zeng Yaohui, Ding Tianxing, Jiao Siyuan, Chen Yuheng, and Tang Jiachen, Zhang Yangzi, Fang Haoquan, and Liu Yaowei. And also I want to mention all the testers of our competition. They give us valuable advices on the whole problem set, and they helped us to find all the minor issues appeared in our first draft of the problem set. And in fact, we made tens of revisions on our whole problem set, and we changed numerous of problems to improve the feelings of all contestants. This cannot be possible with the testers' help. The testers are 杜于浩、蒋凌宇、江澄、陈诺、严子轩、彭博、武林、朱鹏瑞、李清扬、Brian 薛、冯启玉、刘佳宁、朱泽木、裘佳明、范思哲、史浩佳、曹丽、夏鹤鸣、司修远、郭玉哲 and 戴江奇. He said he will test the contest tonight. So yeah, he promised me to test a week before, but he promised me to test tonight. So let's see what will happen on his testing. So give them applause. Thank you very much. And
Okay, my turn. So Qingyue and I was going to prepare a long speech, but it turns out that the conference is long enough and we are too lazy and too tired. And more importantly, we think the closing ceremony belongs to the people who work hard for the whole event and all the contestants and our guests. So Qingyue has credited all the problem setter and testers. There are infinite Chinese names that you may not recognize some of them, but all of them has done a great contribution to the contest. And this is basically the best we can do for now, and we do hope to do better in next time. Now it's my honor to recognize our technical committee members, including all the technical support members and also the live streaming support. They are Cai Shengliang, Pan Lizhi, Pan Haojun, Yang Liangzheng, Zhou Chunran, Dai Longrao, Huang Wenhan, Lydia Proskaya. Please come to the stage if you are still around. Thank you so much for everything. And I know for the challenge, for the contest, and also for all this live streaming globally, and you have done a great job. Thank you so much. Please be seated. Thank you. 要拍照吗？ OK. 是。 And now let me introduce part of the organizing committee and volunteers. They are Nick Wu, Bartosz Toska, Mang Qiuyang, Peng Bo, Chen Junjie, and Wang Chunyang. Please come to the stage. Thank you so much for helping us to organize this event and make sure everything is run smoothly. And so also some of the people here, not just helping to treat our guests and contestants, they also help us test the contest and also the challenge. So without them, none of this will work and none of this will come to today's success. Thank you very much, and we hope to see you soon. Now please be seated. Lastly, let me formally introduce and recognize our contest director, Tan Jie, and two contest director assistants, Ni Yuying, Feng Hongnan, and also our best friends from Huawei, Yang Zhuo, Song Ziwei, Zhang Lingtong, Zhou Wenjuan. Please come to the stage. This event will not succeed without the great efforts from all of you. And we do understand that you have suffered from great stress these days, or maybe the past half a year. But on behalf of the Universal Cup, and also I think we can say that on behalf of all contestants and guests, we want to let you know that we really appreciate your work and very grateful for everything you did in the past half a year. It's our great honor to have all of you in the community. Thank you so much. Some of you may know that my opening ceremony speech is somehow a nice talk, but in fact, I was missing one paragraph, and I don't know why. Maybe I was too nervous, or maybe I just slept for 2 hours and I just skipped that paragraph. But somehow, maybe coincidentally, that paragraph, that part of word is better matching for the closing ceremony. So I will make it as the last for our speech together. Ladies and gentlemen, my beloved friends, every journey has an end, but the good memory and friendship, the bond, the relationship we establish will not fade away as time goes by. I hope this event can further open the bright future of the community. So, we do know that this event is not perfect, and we don't want to view today's on-site finals as a sign of success. For us, it's more of a confirmation that our efforts over the past 2 years have gained the recognition from the contestant, from the industry, or maybe from the academia. But the Universal Cup still has a long way to go and a lot to accomplish. Continuity and survival remain our primary goals for now. We are working on building a reasonable system to make everything sustainable. Only then can we focus on development, allowing more talented individuals to bring their ideas to life with us and help the community grow in more diverse ways. This is difficult, and I know it's really difficult. That's why we need to work incredibly hard, and more importantly, we need to work together with everyone here. One world, one dream. This was the slogan of the 2008 Beijing Olympic Games, and I believe it also applies to us. It aligns perfectly with the mission of the Universal Cup, since in today's world, conflicts are gradually intensifying, and such a message may be rare. But we are willing to dedicate all our passion and energy to deliver it, and we also hope everyone here, or everyone who is watching this live stream, can receive this message. We hope you can consider joining us, seeking and exploring the possibilities for making the competitive programming community better. Thank you so much, and hope to see you guys soon.
Thank you, President Jinbang and Qingyu. Let us thank all staff and volunteers for their efforts in making this event a success. It's time to invite Mr. Li Mingzhen from Huawei to the stage to give out the awards from the Tech Arena Challenge.
Hello, everyone. Welcome to the Huawei Tech Arena's the 2025 Universal Cup Final Challenge awarding ceremony. It's the first part of the exciting time is begin. And before we announce the prize, we first revise the prize level. The gold levels for rank 1 with €8,000, and silver medals for rank 2 to rank 3 with €3,000, and bronze medal for rank 4 to rank 7 with €2,000. And after the challenge contest, we judge all the submissions of all the teams, and with 10 tickets. As you know, 2 of them is a published tickets and shared in the statements, and 2 of them is the tickets for the pretext. And the total score in the final text is 1,000. That means 100 score per ticket. Okay, now it's the exciting time. It begins. Let's first we announce the bronze medal. Okay, let's welcome team USA 1. They get 885 score. Okay, let's go to the stage. And the second team is the Homama overall. They get 860 score. And the third team is Amstel Park. They also get 860 score. And the fourth team is Open Your Minds. They get 836. Okay, let's welcome our guests, Feng Wen and Ben Yong Wang, go to the stage to present the awards to the teams. Yeah, 给他们颁奖。Okay, let's take a photo. Okay, congratulations then again. Congratulations. Okay, let's go back to the seats. Thank you. Okay, next we announce the Civils Medal. There are 10 team names, and Yokipaki. 10 team name only has one contestant, and he gets a 925 score, and Yokipaki gets 900 score. Okay, let's welcome Hong Bo Zhang and Xiao Junwu go to stage to present the awards to the team. Welcome. Congratulations, and go back to the seats. And next, it's most exciting times. We will announce the winner. Can you guess who is the winner? Okay, let's show the winner. They are from Shanghai. They are team Nemesis. They get nearly all the score. They get 990 score. Let's welcome our guest, Qin Liu, go to stage and to present the awards to the team. Congratulations again. And now we have to announce all the gold medals, all the gold medal, silver medal, and bronze medal. And next, we will show you the final scoreboard. Please look at the screen. Yes, you can take a photo. Okay, next is the prize time. We also provide 3 extra prizes. We call the honor medals to 3 more teams. They are Lake Road, UT aka IS, and Chi. Please go to stage to get a honorable medal. Please get on the stage. Okay, let's welcome our guests. Derek Lee and Jing Bangchen go to stage to present awards. Derek Lee and Jing Bangchen. Okay, let's take a photo. Okay, thank you again, and I hope we have more time to meet you again, because we have provided so many online challenges. We also provide some on-site challenge powered by Huawei, you had chance, I hope you can join it and enjoy it. I hope maybe soon we can see you again. Thank you. Thank you.
Thank you, Mr. Li Mingzhen. And next, please enjoy our event video. Okay, the moment we have all been waiting for. Join me in welcome Mr. Qing Yushi and Mr. Jin Bangchen to lead the resolver, where we will unveil the ranking in real time and celebrate each team's achievement.
Qingyu, do we need an argument first before the resolving of the scoreboard? Do we need to fight each other? Okay, no?
Okay, so, come on, please. We're going to unfreeze the scoreboard, and here I take the official mascot of the Universal Cup Finals. Yeah, this is Bai Tianli, and we're going to resolve all the teams. But before we start, I will try to explain the awarding rules. We're going to provide 3 gold medals, 4 silver medals, 5 bronze medals, and all the teams that solved at least one problem will be rewarded as an honorable mention. So is it clear? Okay, so let's just start. So we're going to unfreeze all the onsite teams. So we have like 500 teams participated in the online mirror, but that's just too many, and we won't unfreeze their results. So on the onsite, we have 20 teams, and so every team has solved problem I. And for other teams, I think every team has some pending submissions, so let's just check it out. So first of all is the team TRITR. They have 2 pending submissions. So the first one is the pending submission on problem F, and they made 4 attempts. The last one is just 1 minute before the contest ends. So let's see what happens. And no, it's a no. But they still have 1 shot, and it's a yes. Congratulations. So they solved 3 problems in total. And so they got the 20th place with an honorable mention. And then is the team 没对要. They also have 2 pending submissions. The first one is okay, and the second one is also okay. Wait, it's screening. Like, oh, wait. First of all, wait a second. Wait, no, I didn't post anything. What? What was happening? No. Seems the scoreboard wants the job finished quickly, but that's not what we would expect. So please wait a second and let the technical staff fix everything. Yeah, please restart. Please restart. No! It spoils everything. Okay, it's okay. So let's just restart. Seems the resolver wants to finish his job. Yeah, so let's just restart. Wait a second. Okay, so please wait a second. Seems there were some technical issues there. So we're glad that those technical issues didn't appear during our official contest.
Okay, Qingyu, let me ask you a question. So what was your expectation on the bronze medal cutoff?
Well, it's an interesting one because, at our first revision of the problem sets, we expect to have it should be a 5, 6, 8, 9, which means we expect the bronze medal should be 5 problems, and we want the silver medal to be 6, gold medals to be 8 or 9, and the champion should get 9 or 10 or 11. Well, but just on our first revision, we asked Jiang Lingyu to test our problem sets. And he tried very hard, and he solved 4 problems in the end. So obviously that was too difficult, and we made several revisions after all the testers. We replaced some tasks with easier ones. We want just to maintain the cutoff to be 5, 6, 7, 9. So our idea is all of the 20 teams, you are very strong. And we want to have more problems in the medium difficulty range, to distinguish the teams. And we shouldn't have 5 div 1As or just some fairly easy ones. And I won't spoil it, but you can just guess what will be the actual cutoff for our competition.
Well, I hope the result can match your expectation. Okay,
Yeah.
since it's still not ready, let me ask you a second question.
Seems our mosquito isn't really working.
Is there any problem that under or above your expectation, like the first solving time or not being solving at all? Is there any problem like that?
Well, so first of all, the problem I was replaced we want every team could solve it in the first hour. Please fix it, and we'll just continue. And so we set problem I for this purpose, and then we don't have an expectation which problem teams would try because I think you can feel that most of the problems are in a very similar difficulty range, just with different topics. And so our goal is just that after just finish the easiest one, you can just try different types of tasks. And we didn't even set a killer. We expect every task should be solvable, including the problem G. There's no single submission during the contest, but we expect it is also solvable. When we are choosing the tasks, we give a difficulty tag for each of the individual problem, and I believe problem G is somewhat marked as medium or hard. And there's one interesting thing is, the problem D, the Nurikabe puzzle. So it came up when I was sleeping. When I was sleeping, after finished a puzzle contest, I got sleep and I just, I got setting a Nurikabe task in my dream. And our first revision is we have 2 numbers as the statement side. So we want to set a task with 2 clues, but it turns out it's not solvable. At least we cannot solve it. So, and there's a classic problem called phenomenon in the Asia EC Finals 2020. And so the initial version is also you are given 3 clues and you are going to fill the another type of puzzle, but it turns out it's impossible to solve it. So it was nerfed to have a Toreto grid. So the same thing happens. Like we tried hard to solve the 2 clues version and we cannot solve it. But I was wondering, like 2 clues are almost unsolvable, but 1 clue is fairly easy. So I think this should be the easiest problem in this problem set. And before the testing, I was expecting like every team should solve problem D in half an hour. So obviously, in the end, the first solving this problem is somewhat like in 2 hours or 2.5. So I don't really know, but just when I was creating this task, I found there were many dirty cases. Thus, it's not as easy as we could imagine. So that's a bit about expectation. And I think another good job is done by Andrew. Like he solved problem H in the first hour of the contest. And so yeah, he's the author. And when I was talking with him, like, when do you expect the first team will solve it? And what was your answer?
I think I made the problem about 2 years ago, and at that time I think it should be quite hard. And 1 year ago, there's a secret blog post about some part of the code you can use, and so this problem becomes more solvable. And know that you can use internet and chatbots. And
So the story is, Elijah proposed this problem like 2 years ago when I was setting an ICPC regional. And obviously, we cannot use this problem because it is too hard. And we just postponed it. And this task was unused for 2 years because we cannot find a contest to really use it. Because first of all, it's hard. And if there's no internet access, you basically should do everything on your hands. So I think the best fit for the competition is the Universal Cup Finals. And on the semifinals, since we already had another algebraic problem, so we didn't use it. So we just deferred it to the finals. And that's why we truly use them. And we didn't expect this can be solved too quickly. I mean, just we can imagine it can be solved, like maybe by Homama or USA 1 in the 3rd hour of the contest. But since Andrew solved it in the 1st hour, and when we were doing streams, we just found that a lot of teams are just searching on Google, on Math Exchange, on other things. Yeah, so it's kind of crazy, and maybe the scoreboard is a little bit affected due to this. Yeah, but anyway, so after talking some random fun facts, our scoreboard is finally coming back.
Right.
So
let's congratulate again.
So let's just forgot everything. We didn't remember the results now. So we have Meidun, they have solved 5 problems, then they got to the 12th place. Yeah, okay. And then Japan a few numbers, okay. And then almost doesn't have the 1 penny summation on F, and that's okay. And then for our champion of the challenge, they have an F. Is it okay? Oh, congratulations. And then the team Yoki Parky, they have 2 submissions on C. Oh, it's also okay. So then it's Team Amstel Park. They didn't have any further submissions. So they solved 4 problems in total, and they got the 19th place and an honorable mention award. And then it's the team Open Your Brain. This is the Peking U team, and they have 3 problems on D and 1 submission on J. Oh, it's a yes. Congratulations. And then it's the team PPP. They got the first blood on the contest, and they solved 5 problems in total. So it's 18th place. Congratulations. Yeah, so wait a second. So for all the teams I mentioned, you should just come to the stage at the corner, and we are going to give an award to your team. So Yeah, so then it's the team Japan 406364961. So what's the meaning of this number? Okay, so they got the 17th place. And then is the team 没对要. They solved 5 problems in total. And so they got the 16th place and with an honorable mention. And then is the team Yoki Paki. They have 1. Okay, so they passed it very quickly before I announced. So that's a good job. And then is the team Nemesis. And they solved 5 problems in total, and they got the 15th place in the contest. Well done. Yeah. So then is the team almost retired handling. They have 1 mission on K. Yes or no. So they solved 5 problems in total with the 14th place. Yeah, and then is the Peking U team Lally Road. They got 2nd place on the World Finals. And they have 4 submissions on K, which is no. Okay, so they got 13th place. And so according to our rules, these are all the teams who achieved the honorable mentions. So, wait, honorable mention 的名单吗 ？honorable mention 的名单没？猜对不是射了吗 ？Okay, so anyway, oh my God, can you just stop it? Come on. Okay, so for all teams above, please come to the stage. Please come to the stage for all the honorable mentions teams.
Yeah, please come to the stage. And I also invite Mr. Xiaojun Wu and Nick Wu and Bartosz Koska. Please come to the stage and help us to present the honorable mentions to all the contestants. Please come to the stage. Congratulations. Okay, thank you so much. Please be seated.
还是不能用。So, okay, so it's a bit of nightmare, but it's a bit of mess, but let's just continue. And we are going to the medals. So the first team in the medals is the team Open Your Brain. So they have no further submissions, and they solved 5 problems in total. So congratulations, they are the first team who got a bronze medal, and they are also the team who will represent Peking University to the next World Finals. So congratulations.
Please come to the stage.
Please come to the stage. Please come to the stage.
And I will invite Mr. Yuanlong Zhang from Huawei and Mr. Han Haojun from the Universal Cup to present the bronze awards to the teams.
Where's one person?
Congratulations.
Let's move on. So
our guest,
the
please.
next team is the UT AKAs, and they still have 1 pending submission on problem K. So let's just see what will happen. It's a no. Okay, so they just solved 5 problems in the end, and they are the second team who got a bronze medal. Congratulations! Please come to the stage. That's awesome, and let's move on to the next team. So the next team is a team lunch break at 4:30. They have 2 pending submissions. The first one is at problem D, and the result is no, it's an incorrect submission. And the next one is 2 pending submissions on problem K, and the result is also no. So they solved 5 problems in the end, and they got 10th place. Congratulations, and please come to the stage. Okay. So let's move on to the next team. So the next team is Team 9 Birds. It's also a team from Peking University. So we have 3 teams from Peking University in total. That's incredible. And they also won the world champion title on the 40th ICPC World Finals. And they still have 2 pending submissions. So the first one is the problem K. They have 1 submission on the last minute of the contest. And let's see what will happen. The result is no. Okay, so, and they also have 1 additional submission on problem M. And the result is, oh, it's also no. Okay, so, but it's a great job. And they got the 9th place with a bronze medal. Congratulations, and please come to the stage.
Okay, congratulations. Please be seated.
Okay, so then, wait a second. Okay. So, well, it's okay. So, let's just move on. So, the next team is the Team 10 team name. And this is amazing because they only have 1 team member in his team. And the only team member in this team is Liu Hengxi. And he's the winner of the IOI 2024 China team selection. And he, 2025 China team selection. And he will represent China to participate in IOI 2025. And they solved 5 problems in total. And he got a bronze medal. Congratulations.
Whoa!
Woo!
Congratulations and good luck in IOI.
Yeah, good luck on IOI. Okay, so that's all the teams with the bronze medal. And then let's end the zone with silver medals. So the first team is Zhiyuan Star, and it's also a team formed by 3 high school students. And they have 2 problems with pending submission. So the first one is problem H with 2 pending submissions in the last minute. So as the author, do you think they can pass? Okay, so he said, So it's probably not. And let's see what will happen. It's a no. White guy. And then they have 5 pending submissions on problem I. So is it a yes? Yes! Congratulations! So they solved 6 problems in the end. It's well done. So then let's just go to the Polish Mafia. And they also have 3 penny submissions on problem D, and let's see what will happen. So the answer is yes! Woo! It's amazing.
So all the silver medal has at least 6 problems, right? Does that match your expectation?
Yeah, it's good job. Thank you. And let's just see. So the next team is Yoki Parking, and since they don't have any penny submission, so in the end they solved 6 problems. Well done, and they received a silver medal in the contest. So please come to the stage.
Let me invite Mr. Fan Fan from Huawei and our contest director Tan Jie from Universal Cup to present the silver medals to our contestants. Congratulations, please be seated. Our guests, please stay on the stage.
Okay. Woo! Okay, it's really nice. So, thank you, Musket. And then let's just go to the next team. It's Dove Portif Vetra. Sorry if I pronounced it wrong. And they have 3 penny submissions on problem K. And the verdict is no. So they solved 6 problems in the end, and they got the 6th place with a silver medal. Congratulations! Please come to the stage.
Congratulations, please be seated.
Okay, so let's move on. And we have the team Zhiyuan Star. And since they don't have any further penny submissions, so they solved 6 problems in the end with the 5th place. It's so amazing, like, it's a high school team, and they solved 6, and they beat so many great teams. Congratulations, very well done. And please come to the stage. Okay, so finally we have one last silver medal sport. And clearly, since there's no further pending submissions, it will be awarded to the team Polish Mafia. And they solved 6 problems in total, and they got the 4th place. Congratulations, and please come to the stage.
Congratulations, please be seated.
Okay, so now is the most exciting moment. We're going to announce the winner of the gold medals. And as you can see, we have 3 gold medal sports and we have 3 trophies there. And in Chinese, we have 3 words called 冠军, 亚军, and 季军, which means the champion, the runner-up, and the 3rd place. So everyone wins a gold medal will also got a trophy with their place. And so as you can see, we have 3 legendary teams. I think a lot of people can just predict they will win a trophy. But let's just see who will win the contest. So first of all, it's team 03 Slimes. And all the team members in this team are going to study at MIT. So that's also an MIT team. And you know, in the beginning of the contest, they are not doing very well, just like what did MIT did in the last World Finals. But they just adjust their status and they got very well in the middle of the contest. And let's see what will happen in the end. So they have 1, 2, 3. They have 3 problems impending. And let's just see the first one. It's problem B. They had 4 submissions. And let's see what will happen. The status is yes! Congratulations! They solved 8 problems now. So it means we have 1 solved on problem B. So the only unsolved problem in this contest is problem A and problem G without any reasonable submissions. So you know, in our prediction, we thought at least the G will be solved by like 2 or 3 teams. So yeah, but anyway, congratulations. And then let's move on to our Japanese friends, Homama OVO, and they also have 2 pending submissions. So the first one is 1 pending submission on problem E, you know, on the last 2 minutes of the contest. So can they solve this? And the answer is no. Okay, it's fine. And they also have 7 additional submissions on problem F. And it's also interesting, you know, the last 3 minutes of the contest. So let's see what will happen. And the verdict is yes! Oh! Well done! So as you can see, all the teams in the gold medal zone have solved at least 8 problems. So the gold medals are very competitive and they are going to just fight for the trophy of the contest. So let's move back to 03 Slimes. They still have 2 pending submissions. So the first one is 1 submission on problem E. And let's see what will happen. So the verdict is no. Okay, it's fine. But they still have 1 more pending submission on problem H. And will they solve this? The answer is yes! So they are leading the contest now. It's really amazing. And so they have released all their submissions, but we haven't talked a single bit about USC 1. So let's just move on. But now, since Homama has no further pending submissions, it means they solved 8 problems in the end, and they got the 3rd place of the contest. Congratulations, and please come to the stage.
Let me welcome Mr. Xun Liu from Huawei and Mr. Jianglin Yu from the Universal Cup to present the gold medals and the trophy to their team. Congratulations. Congratulations, our second runner-up. Please be seated.
Wow, that's so amazing. And the exciting moment hasn't stopped yet because this is USA 1 and they even have 3 pending submissions. So let's see what will happen. So the first one is problem B. They had 1 pending submission on the last minute of the contest, and the verdict is no, it's a no. Okay, so it's fine because they have 2 more chances to go. And then they have 3 pending submissions on problem D. And you know, it's the Lunikami puzzle, and I know they have some puzzle masters. So will they eventually solve it? And the answer is yes! So they also solved 9 problems now. And they still have 1 pending submissions. But since 0 submission line has no further submission in total, so it means they solved 9 problems and they got the 2nd place of the contest. Congratulations! And please come to the stage.
Congratulations, please be seated. Our 2nd place runner-up.
Okay, so obviously we know that USA won the contest as usual. So shame on you, you made this contest full of photos, but you know there's one final story. So they have 2 pending submissions on problem K. And the verdict of those submissions will mean will they win a contest by solving one more problem, or just by some nice penalty. So our final question is, can they solve problem K? And the answer is yes! So they solved 10 problems in total. So obviously, they secured their place on the 2nd Universal Cup Finals, and they are the champion of the 2nd season of the Universal Cup. Congratulations!
Congratulations! Congratulations. And I think this concludes the 2025 Universal Cup Finals. Hopefully we can see all of you soon and wish you a very good evening and please enjoy the remainder of the event. Thank you so much for attending the finals and the closing ceremony. Thank you so much.
So it's over now, and so you guys can just
Okay, it's
take a
over
break.
and we will be proceed to the dinner time. Thank you for attending today's long day. I understand. Thank you so much.
Yeah. Woo!
Yeah, you may free to take photos here, and we have photographers, and we will soon tell you about where to go and how to proceed. There's nothing left, so you can do whatever you want here, and if you want the flag, you can just get it and